So welcome to this session on Introduction to Biostatistics. And I am Tinku Thomas. I am a professor of biostatistics at St. John's Medical College in Bangalore, which is in South India. And I'm very happy to see this big group over here representing different parts of the world, different countries. Thank you for joining in for this course. So you already have covered one session, I think, on data science, and what from the participant description I had received, many of you already have some exposure to statistics or to data science. But since this is much of an introductory course, I will go through the basics of biostatistics, which is my area of expertise. And since this is a course which is focusing on the application of data science to the health, and public health and health systems, we will focus on biostatistics. Okay, so let me just share my screen. I hope all of you can hear me well enough. If there is any difficulty in hearing me, please let me know. Okay, thank you. Is this visible in slideshow?
Yes, ma'am, it's visible.
Okay, thank you. So this first session, so we have 4 sessions planned in this today's class. And the first one is to deal with the descriptive statistics, which is the most basic of all, statistical procedures. And going on, we will have inferential statistics, non-parametric statistics, and we will wind up with a session on sample size calculation, where we will try to do a few practical examples also. Okay, so that will be towards later in the day. So, so before we start into what statistics, why we use and how, which one to pick and so on, a basic question of why should we even use statistics. One second, let me just align my bar, okay, so that I can see what is on my screen. Okay, so the question is, why should we even do statistical analysis on data? So here is an example where, you will notice that a lot of my examples are coming from the area of nutrition and clinical studies, because that is where I work. And here is an example of a study where they looked at infant survival with respect to the level of care the mother received in an antenatal, in an antenatal care service. So there are 2 groups: a group that received less care and another group that received more care. And the outcome of interest was to look at mortality in infants. And the data showed that there was 5% mortality in the less care group and 2% mortality in the more care group. So by looking at this data, it looks as though there is some difference. There is a reduced mortality in the more care group. And our inclination is to think that, yes, more care is beneficial. But if you examine the numbers that were studied, they are not too big. So we have 393 people who received less care and 322 people who received more care, out of which only 20 mortality in the less care group versus 6 mortality in the more care group. But we can see that the denominators were different, and therefore the percentage difference is not as magnified as a difference of 20 versus 6, a percentage difference of 3 percentage point difference. And the question is this particular to this particular sample that was drawn in the study, or can this be generalized? Is it possible that if anywhere this kind of care in the larger population, if this kind of care is given, that is women given more care during the prenatal period, is it likely that the mortality would be reduced by about 3 percentage points? So that is a question. But right now, we don't have the liberty of examining the entire population. And all we have to do is to infer based on the data that is available from the sample. And that is where statistics come in to be useful to tell us what is the chance of us getting this particular difference of 3 percentage points in reduced mortality in more care group as opposed to the less care group. And if we eliminate the chance, then we really understand, is it possible even? So in order to have evidence-based practices in clinical practice or in public health practice, it is important to understand what is true and what is due to chance. And statistical techniques help us in making this kind of a conclusion and keeping aside the chance factor to decide whether this observed difference in this sample of 3 percentage point in mortality, is it true or not? Okay. So statistics methods, although many people, mostly those who are practicing clinicians or doing health research, they are not very much aware as to where the statistics is applied. Usually the concept is that once you have the data, that is when it is time to apply statistical techniques. But in fact, statistical techniques come into application even at the study design, because even while drafting a study objective, it is important to think how exactly you are going to measure, or how are you going to summarize the data, and therefore how do I state the objective of the study research. So even at the study design, then coming to the sample size calculation, again, many people don't really understand as to why it is important to calculate sample size, and therefore they ignore that. So statistical techniques actually has to be applied at the very beginning, that is in the study design phase itself. And of course, in the data collection, how exactly you are going to collect the data, in what form, in what is the kind of variable that you will consider. There again, it is important to think how exactly are you going to use the data, because the way you collect the data should be based on how exactly the data is going to be used. There's no point in collecting data that's not going to be used later for informing towards your research question. So that is important. Then essentially for analysis, yes, everybody accepts that statistical techniques are applied in the analysis of the data and interpretation, because it's not enough that you know how to make a few clicks on a software and get some results. You should know what to interpret what you have got there. And finally, presentation of data. This is again critical, because how exactly will you pass on this information to an audience who is interested in the question that you had asked? There are different ways of presentation, where if you are writing a report, then there's a certain way of presenting the data in a more detailed form, as opposed to a manuscript or a journal article where you have to make a very concise presentation of the data, but essentially not losing any critical information also. So statistical techniques are very important in all of these aspects of research. And therefore, it is a systematic way of doing research. So biostatistics is nothing but the application of statistical techniques to scientific research in health and health-related fields. So that is medicine, epidemiology, public health. When you apply statistical techniques, we call it biostatistics. Otherwise, the techniques are all the same across different, different areas like economics. There are some differences in names that are used for the same techniques. The terminology may be slightly different, but otherwise the techniques are more or less the same across any field that you use statistics. So to start off, it's very important to understand what is the nature of the data that you're using. So you can actually classify data in many different ways, but it's easy to just classify data as quantitative and qualitative, where qualitative is not really, something that you really measure, but observe. So for example, disease status, whether present or absent, you don't have an absolute measure of the disease status. It is just classifying individuals as being disease present or absent. Or if you want to put the country of your residence, so that is again a qualitative information. Whereas when you can record information as numbers or measures, then we call it as quantitative data. It is important to understand or differentiate between these, because the way you will treat the data henceforth would depend on the nature of the data. So we can further classify. We can call data as being discrete or continuous. So even if you have data recorded as numbers, it could be discrete data. That means it can only take some fixed numbers. It cannot take any value. The example given here is number of times milk is consumed in a day. So it can be 0 times, 1 time, 2 times, 3 times, and maybe maximum of 5 times, or let's say 20 times even. But they are just some fixed values that can be true data for this particular variable of number of times milk is consumed in a day. So what we call as continuous is it can vary, and it can be any value between a certain range. For example, quantity of milk consumed in a day. So that can be any value. So let's say it could be 0, or it could be 500 milliliters, and it can be any value within that range. And that is a continuous data, because it can take any value within a certain range. So this is another way of classifying variables as being discrete and continuous. If we want to be further specific about the kinds of data, we can classify them as different scales of measurement. This is important in some kind of analysis that we will do. And I have not gone to the last 2 classes, which is interval and ratio scale. I don't want to put much attention into classifying them as intervention and ratio scale. So I'm clubbing it and calling it as continuous. But the initial ones, that is nominal. Nominal is when, like, for example, we had seen earlier, place of residence is a nominal variable. There is no particular magnitude and there is no particular order. So it is a nominal scale. So that is nominal. In ordinal scale, what happens is there is a particular order in which the categories appear, but there is, okay, that's a mistake over there. So there is no magnitude actually. There's no magnitude, but the order is present. Excuse me for the mistake, that it should actually read as order. So the order is there. For example, grade of anemia. So if we are categorizing individuals into different grades of anemia, we could classify them as mild, moderate, and severe. And we know that severe anemia is of a higher grade as opposed to mild anemia. Therefore, the grades of anemia is an ordinal variable. And there are certain different ways in which we can use that nature of the data. That is the ordinal nature of the data. So that is an ordinal variable. And continuous data is many things that you measure in your research. That is, like in this case, hemoglobin, weight, height. You can think of any number of examples for continuous scale measurements. And as I mentioned earlier, it could be any value within a certain range. So this is important to keep in mind, because the way you will summarize the data and later analyze the data would depend upon the type of data that you have. Also, how the way you will collect the data also depends on the type of data that you will have. So once you have the data, again, how you would represent the data also depends on the type of data. For some things, you can summarize by, let's say, some summary measures such as mean and standard deviation, but some things you cannot. Whether you prefer to present something as tables or diagrams also depends on the nature of the data. So we will quickly go into the ways of summarizing data. And one of the important measures that help us to summarize data is a measure of central tendency. So from the word central tendency, we understand that central tendency is a measure that tells us about a central value in the data. So what do we mean by a central value, and why are we looking for a central value? Because we expect that the value that is towards the center is representative for the rest of the data. So if somebody asks us to describe the data that we have collected, then it is very hard for us to list out each and every data. See, we have, say, 100 people data we have collected. It is hard for us to list out each per individual's data. Moreover, it is not necessary also. Plus, it is not informative. So even if we can list out each of the data, it is not going to help the person who is listening to you or who is looking at your data, because it is not telling him anything. So it is not at all helpful. So what we need is one summary statistic for the data and the measures of central tendency. There are many of them. The measures of central tendency help us to summarize the data, okay? So the most common measure of central tendency that we use is the arithmetic mean. Then we have the median, the geometric mean, the harmonic mean. There are different kinds of measures of central tendency. And why we have these different measures of central tendency is because the context in which we apply each of them differs. We do not apply geometric mean to all kinds of data. We do not apply arithmetic mean to all kinds of data. There are certain characteristics of the data that tell us this is a more appropriate measure of central tendency compared to the other measures of central tendency that are available. And that is why it is important to understand the measures of central tendency. So arithmetic mean is something that you are all familiar with. So it is nothing but the sum of all the individual values divided by the number of observations. In this case, you can see that I'm calculating the arithmetic mean of weight, which is giving me a value of 29.02 kilograms. So I can summarize, I can say that, okay, for the data that I collected, the mean, the average mean is 29. And somebody immediately understands, okay, that is where the central value of the data is. And that is informative. So if we were to plot it in what is called a histogram in this case, where the bars are all touching each other, and this is a plot for a continuous data, you can see that it is at 29.02. But you might think that maybe it is not really the measure of central tendency in this case. It may not be really lying towards the center of the data. You can have such a feeling. And therefore, we can look at another measure of central tendency, which is called the median. So median, by definition, is a value that lies at the center. So it is that value that has 1/2 of the number of observations lying above it, and another half of the observations lying below it. So essentially, median is at the center of the data. So what do we have to do? We have to arrange the data in either ascending or descending order and identify the middle value. And what is the advantage of having the median? So this is essentially a set of data to show how the median is calculated. And you can see that the 8th value, in this case, when we arrange the data, it is 56 is the median value. Okay, so now when we plot that for our previous data for weight, we can see that maybe the median is a better representation of the measure of central tendency for this data, but essentially there is no much difference between the median and the mean. They are quite close to each other. Now, if you were to take the mode, which is the most frequently occurring data, you can see that it is somewhere around 20, the most frequently occurring value, but that may not be the best measure of central tendency, although it is the simplest of all. So we have seen 3 measures of central tendency which can be used, of which mean and median are the recommended ones. But then we also have to look at how the data is spread around this mean or median, which is also very important because the mean gives us an idea of only that central value. But how much spread is there of other data points around mean is what we need to understand, and the measures of dispersion, and the word dispersion says spread, or help us to understand that. So the simplest of the measures of dispersion is the range, which is the difference between the highest and the lowest number in the data that you have. But there are, although it is the simplest, it has disadvantages because as you can see here in this example, there are 4 values which have value 4 and there is a 50, but the range is 46, as opposed to the next set of data where there is a lot of variability in the data. Even then the range is 46. So both of them having a range of 46 or a measure of dispersion of 46. But you can, by just looking at the data, tell that, yeah, the first one is less dispersed than the next one. There is a lot more variation in the data. Okay, so range is not that good a measure of dispersion. And therefore, we will look at something that is a little more within the data, which is the interquartile range. So essentially, the interquartile range calculates the difference between the lowest and the upper quartile of the data. That means the range of the middle 50% of the data is what is an interquartile range. So we need to split the data into 4 equal parts and the range of the middle 50%. That is the value that is lower quartile and the upper quartile. The difference between the upper and the lower quartile gives you an understanding of what is the range of the middle 50% of the data. And that is essentially your interquartile range. So for the fact that the second quartile of a data is nothing but the median. The second quartile is the value that corresponds to the 50th percentile of the data. It is nothing but the median. This measure of central of dispersion, which is interquartile range, goes along with median. So if you are reporting median for any data, you should measure interquartile range and report interquartile range alongside median to give an understanding of the measure of central tendency, central tendency and measure of dispersion. So now, if you look at standard deviation, that is another measure of dispersion, which gives you an understanding of, okay, how much of variability about the mean. So we have another measure of central tendency and we have a measure of dispersion, which is standard deviation. It gives us an average variation about the mean. So if somebody is reporting mean, it is good to report standard deviation along with mean because it is an average variation about the mean. So yeah, this is the formula just to indicate that it is a variation about the mean. But how exactly would you interpret? So the interpretation is with respect, always with respect to the mean. That is, if the standard deviation is low with respect to the mean, then we know that there is very little variability. As opposed to a large standard deviation about the mean, then we know that there's a lot of variability. So what do you really mean by low variability and high variability is what we will try to understand. Now, the first thing is the lowest value that standard deviation can take is 0, which means that all your data are the same. There's no variability. Okay, it cannot be a negative value. So then we try to understand SD with respect to the mean. A value of SD which is as high as the mean or even greater than 50% of the mean is something that we would consider as high variability. So here we are just showing a conversion of SD with respect to the interquartile range. So you can approximate the interquartile range to an SD by this calculation. That is the quartile 3 minus quartile 1 divided by 1.35. Sometimes you have to use the SD and what is reported is only the interquartile range. Then you can use that to use in the calculation that you have. So this is just a conversion. But again, trying to understand what is a small SD with respect to the large SD. So can we can just consider as a rule of thumb that an SD that is higher than half the mean can be to some extent considered as a large SD, and therefore a small SD would be an SD that is lower than 50% of the mean or half the mean. So that is quite useful as a rule of thumb for many cases that we will see hereafter, where a condition is required on how much SD is there. So we just keep that in mind while we go through the rest of the session. Okay. So now this is just a summary. We have different kinds of data. Sometimes for ordinal data, we can calculate the median, but only when continuous data, we can calculate mean. We cannot calculate mean in either nominal or ordinal data. Okay. So let us say that we have very few data, like in this case, just a set of 10 observations. Then we cannot represent, sometimes we cannot represent data, or we needn't represent data as the summary measures. We choose to represent them as graphs because people can understand them better. Various ways. So there is this. This is up to you to present the data in the best possible manner. But this is frequency distribution. That means you're presenting the data that you have as the number of observations that you have. So for example, here in the bottom histogram, you have 194 observations of hemoglobin, and you can see that you're plotting it in a histogram. But this is a frequency distribution. What you have on the y-axis is the number of people who have reported a certain value of hemoglobin. So that is a histogram. Now we'll try to understand what a probability distribution is. Now that was frequency, what we observed out of a sample. But everything has a certain distribution in the larger population from which the sample was drawn. And sometimes we know what that distribution is likely to be. So for example, if we are flipping two fair coins, okay, and then the probability of getting two heads is 0.25 because the probability of two independent heads is 0.5 into 0.5, and therefore the probability of getting two heads while flipping two fair coins is 0.25. Similarly, the probability of getting two tails is 0.25. Therefore, the probability of getting a head or a tail is 0.5. Now, this is understood. This is theoretically what is the probability distribution of flipping two fair coins. But so we can represent it like this. This is the probability. But when you are actually doing an exercise of flipping two coins, it is not necessary that you get it the exact same way. You might get 17 as two heads, 26 flips as two tails, and 57 flips as a head and a tail, not exactly the way we thought it should come. So this is now a frequency distribution. But by looking at the frequency distribution, we see that it is somewhere close to the probability distribution that we started off with. And what happens is, as the number of flips increases, more and more flips, then you will see that it comes close to the probability distribution. Or in other words, when we are coming closer to the population, the probability distribution is more visible. In smaller samples, it is not very easy to observe that probability distribution. Okay. So, but what we know here is that this particular observed distribution of flipping a coin is actually coming from a probability distribution of 0.25, 0.5, and 0.25. Now we know this, but in biology or in health, when we are doing these studies, we don't know what this is. We only have the observed data and we know the frequency distribution. We very definitely don't know what the probability distribution is. But by looking at the the data that, or by the very nature of the variable that we are dealing with, we can have an understanding of what the probability distribution could be. So that is what we are going to see now. So every value, so every random value, for example, every value in a random variable will have a certain probability of occurring. And that the distribution of that is what we call as the probability distribution. So the probabilities will range from 0 to 1, and the sum is always 1. And we can characterize the probability distribution by what we call as a probability density function. So in this case, this is serum albumin, and you can see that when you're observing the frequency in a set of individuals, you get a histogram, which is seem to having a certain pattern. And this pattern, when you actually observe in a larger population, or you are actually drawing it as a probability distribution, we can get a bell-shaped curve, a symmetric inverted curve like this. And this is called a normal distribution or a Gaussian distribution or a bell-shaped distribution. And once we know that this is the distribution that serum albumin follows, there are many utilities of it. There are many things that we can understand from this data, even without really, actually going about observing it. For example, once we know that this is the distribution of probability distribution of serum albumin, we can figure out, okay, what is how many people can have a serum albumin value of less than 20? That is possible, or exactly 20. Now we know that the probability of the value 20 serum albumin is 0.1. That means about 10% of the people in that population would have a serum albumin value of 20. So we can also calculate the cumulative probabilities. So that is useful. Now we need to define what that bell-shaped curve is, and this function over here gives us an understanding of what the value of each of those data points is as probability of occurrence of a value of x. X here means a value of serum albumin. Mu is nothing but the average of the serum albumin, and sigma is the standard deviation of the serum albumin. So essentially, if you know the mean and the standard deviation of the data in the population, then we can figure out, okay, what would be the value of serum albumin of, say, 25 of 30. We can figure that out. So this is a Gaussian distribution. So first and foremost, we should know what is the distribution, what is the nature of the data that it follows, and then we should be able to define that distribution with using some values which are called the parameters of the distribution. In this case, for a Gaussian distribution or a normal distribution, the parameters of the distribution are the mean and the standard deviation. And once we know these, we can define the exact shape of that distribution. Okay. And the properties of that normal curve is it is symmetric about the mean. It has only one mode, which is it is unimodal. The values will extend from minus infinity to plus infinity, and the total area under the curve, that is the overall probability, is 1. So many utilities, as I mentioned earlier, of a data, of us knowing what is the distribution of the data. And in this case, if it follows a normal probability distribution, then there are many utilities. And this is one of the things that we use very commonly, which is a standard normal distribution. And we know that if we calculate mean plus 2SD, then we know that we are covering almost 97.5% of the data to be below that. Or in other words, let me put it in another way. We will have 2.5% of the data lying below mean minus 2SD, and we'll have another 2.5% of the data lying above mean plus 2SD. And this is very, very useful. So 68% of the data would lie between mean plus or minus 1 SD. 95% of the data would lie between mean plus or minus 2 SD. and 99.7% of the data would lie between mean plus or minus 3 SD. Now, just keep in mind that when I said 2 SD, it's rounding up 1.96 SD to be exact. But let's for now keep it as 2 SD. So this is a very useful property of the normal distribution, which can be used in many places, especially by standardizing data. So by just looking, so how do we determine, how do we understand what I keep saying that it is very useful, but if one has to use it, one has to know what the probability distribution is, because not all data will follow this normal distribution. So how do we understand that? So one of the ways to understand is to look at histograms. But unless you have a large sample, you will not be able to see that bell-shaped curve. For example, we have 4 rows of data and all of them are actually from the same population. Okay. The difference is that the first row, each of these 5 plots, they are all random samples of 20 subjects each. Now, if we just see those 20 subjects data, you cannot see any particular pattern. So you're not sure by just looking at that histogram, what is the probability distribution of that? Now, sometimes we know beforehand. For example, since I'm working in the area of nutrition, and if you ask me what is the distribution of weight, I will say it is normally distributed. If you'll ask me what is the distribution of hemoglobin, I'll say it is normally distributed. Sometimes we know because we have seen a lot of data, but sometimes we don't know. And then we have to infer from these distributions. So you see, when you come to 50 samples, then you will see that the gaps are slowly filling in. There might be some pattern or there may not be pattern. We are not so sure. But as the sample size increases to 100 and later to 500, we are clearly seeing the pattern, and it appears as though this data, this sample of 500 is drawn from a population which has data that follows normal distribution. So that is what we need to infer. But as I said earlier, if we have small sample size, by just examining histograms, we cannot have an understanding of what that distribution is. Therefore, we have other methods of doing that. So visual inspection may not be sufficient. So what do? So this is another histogram here in this case of hemoglobin. We can look at the mean and the median. Look at that. So the mean here is 12.4 and the median is 12.5. Now, earlier we said that the normal distribution is symmetric. That means that the mean and the median should coincide. We have 50% of the data below the mean and 50% of the data above the mean. That means the mean and median are coinciding. So this is one indication for us to say whether the data is normally distributed or not. Another indication is that look at the standard deviation. It is quite low in comparison to the mean. If the mean is 12.4, the standard deviation is only 1.2, indicating that this data probably is normally distributed. So this histogram is also quite clear to us because the sample size is pretty large, 3,788. Always doing a plot of the data is very, very useful because it tells you how low the values are, do you have outliers, and so on and so forth. Now, another way to do it is to draw a QQ plot. That means the expected values on a quantile plot, the expected values that should be lying on that straight line if the data follows normal distribution versus what you're observing. And even if the data exactly does not fall on the line, if there are slight deviations at the ends, at the tips, at the lower tip and the higher end, it is fine. We can approximate it to a normal distribution. We can assume the normal probability and then go ahead and do whatever statistical test is appropriate for a normally distributed data. So this is another way of examining the data. So there are many ways. Now this is another histogram. In this case, it is serum ferritin. Now serum ferritin is known to be not normally distributed. It is known to be a variable which is positively skewed. You can see that there is a positive tail to this data. There is no symmetry about the mean. So this is a positively skewed data. And in this case, since the sample size is big, we can clearly observe that in the histogram and say that, yeah, this is not a normally distributed data. But also look at the mean and standard deviation. The mean is 31 and the standard deviation is 28, quite large with respect to the mean. And therefore, that is another indication telling us that this data is probably not normally distributed, even if we cannot observe it in a histogram so neatly like this. And yeah, so look at the QQ plot again, clearly indicating that this data is not normally distributed because the observed data is going far away from the expected values on that straight line. So what do we do in such situation? Look at the median and the mean, quite different. The mean is 31, the median is 23. So there is this clear indication everywhere that this data is not normally distributed. So what one could do is to calculate the log value of serum ferritin, that is a transformation of the data, and then use the transform data for all further calculations. So this is an example here where the log value of serum ferritin is taken, and the mean that you see here is actually a mean of the log. So don't just go by that. That is not right. So this is the x-axis over here is the for the log serum ferritin. Now you see that the data looks more or less symmetric. So sometimes transforming the data. Now this is a QQ plot of the transform data. So transforming the data helps, and then you can get the data to be symmetric and then apply whatever test that you want to apply that is suitable for a normal distribution on a log transform data. So that is also fine. Now look at this example of number of cigarettes smoked. If you look at it, you can see that there are a lot of people who have value 0. There are people who are smoking, and the number of cigarettes are reported. Now, there are many ways of reporting this data. Just to keep in mind that just going by mean and SD will not be a good idea, because this mean and SD are not good representation of the question, what is the number of cigarettes smoked? Okay, I can see a question that so we'll take all the questions later. So let me just continue. Okay. Now, okay. So the median is in this, and now in this very case, if we calculate the median, it turns out to be 0. So what is it telling us? Is it telling us that the median number of cigarettes smoked is 0? It is not very informative. So what probably one will do, there are many ways of doing it, as I said. One way to do it is to just look at the number of people, at the people who are smoking. So the number of people who smoked are 53% of this data over here. And then you can calculate the median number of cigarettes smoked. In this case, 10 cigarettes, and the quartiles are 4 and 14. So the interquartile range is 10. So it is another way of representing the data, a little more informative. Now we'll say, okay, only 53% of the data smoked, and among them the median number of cigarettes smoked is 10, and the quantiles are 4 and 14. So that is a much more informative way. Why I present it here is because many times we see people without really examining the data, presenting the data in like this as median of 0 without realizing that actually there is a problem. They are not telling the whole story. Now look at this. So these are all normal plots. They are symmetric about the mean, and the total area under the curve is 1. All of that is fine, but they're all having differences in terms of their mean and the standard deviation. This blue line over here represents the distribution, the normal distribution, which has the highest SD. And these are all standard, this blue, red, and green are what we call as, normal plots with a mean of 0. They have a mean at 0, but the SDs are varying, and that is why you are seeing curves that are sharp, curves that are flat. This particular purple one is shifted to the left. That means it has a different mean as opposed to the others. So both mean and standard deviation describe the data, even if it is normally distributed. Those are the parameters of the data. So it is important to, involve a statistician right in the beginning of the study. If you are having a study, planning a study, and I'm sure all of you are doing that, and all of you may be actually being on the side that I am, actually analyzing data or looking at it. But if you are a statistician or a person who handles data, be insistent that people come to you at the stage at which people write proposals, they are writing the grants, and start collecting data, thinking about the pro forma, how exactly they are going to collect the data, and so on, so that all these concepts are kept in mind while doing the study right from the beginning. So I'll stop there for this session. I'll take this 1 or 2 questions, I think. Okay, so the question is biostatistics limited to only public health or epidemiology data, or is it related to life sciences? It is applied anywhere. In fact, the agriculture scientists call their area, the statistics that they apply in agriculture, also as biostatistics. So it is not limited. From my perspective in working in health and public health and clinical science, refer to it as the statistics there. The message that I wanted to convey there was that essentially the statistical techniques are the same, and the name difference is only because of the area in which it is applied. Yeah, so, and I think somebody has already replied. So it is not restricted. The next question is, after transforming the data, the sample size reduced? Yes, so I will just go back to, thanks for that question. I will go back to that plot that you are referring to. It is this. You see that it is only 185. The thing is, I have taken a subset and presented the data. I have not presented the whole 3,784. It is only for a subset. The log transform value is presented. So the data has not reduced. It is just that the way I chose to present, I presented it only on 185 subjects. I hope that is clear now. Yes, there is a hand raised, Sean. You can ask your question.
Okay. Good day, ma'am. Can you hear me? Can you hear me, please? Can you hear me, ma'am?
We can hear you.
All right. All right.
Yes, I can. Yes.
Okay. I want to ask, in the field of public health, I've finished my master's in public health, and I have started my PhD in epidemiology. But I asked my professor one day, he was telling me that data science and have no base or have no field in public health. That in public health, what they only know is biostatistics. So because I also want to venture it, so I want to ask: is there a difference between what we do in biostatistics, generally the statistical tests, the modeling that we do, and then data science? Because data has gone beyond, I don't know. I just want to ask, what's your thoughts about that? Is data science now part of public health?
Yeah. So can I repeat your question just to make sure that I got it right? You're asking what is the difference between statistics that is applied in public health versus what is in data science? Is that right?
Yeah. Thank you.
So, so in public health or in any research, particularly when we apply data, we are, let me put that way. In data science, mostly the statistical techniques that are applied are not very complex, but they're all data-driven techniques. So they rely on the data to make the inference. So the probabilistic approach of actually testing and all of them are very few in data science. So that is the difference. So it is very much data. Like, for example, if you think of clustering as a method, the cluster analysis, which can be a good example of how a data-driven approach, all the classifications, everything is based on how the data is arranged. So it is a data-driven approach. So that is a basic difference. But otherwise, statistical techniques that are applied, the techniques that are applied in data science, mostly regression-based techniques like decision trees and whatever, all of them are based in statistics, and the principles of statistics apply. In public health, from whatever experience I have, we are more inclined to explore a particular research question with an understanding of what the data should look like and what it should show us, or we have an understanding of the probability distribution of that particular data, what tests to apply. So we are very much focused in terms of exploring a particular question, and therefore the statistics align to that. Whereas in data science, it is more, you just put in the data and apply a particular tool, and that tool has a basis of any one of the statistical techniques, and it just applies that particular technique. And since the data is usually large in data-driven techniques, you won't flop very much on the assumptions of statistics. So that is generally the approach, in my understanding of the difference. So the tools are not sufficient in public health. I could put it the other way. In data science, the knowledge of the tools that you need to apply. That is why a lot of engineers actually go into data science, because they needn't have a good understanding of statistics per se. They need to have coding experience. They should know how to run the tools, and that would be sufficient for them. Whereas if you are in public health and if you're applying statistics, a good understanding of the basis of statistics, the principles of statistics is required. I hope I answered your question. Yes, there's one more question. Please ask.
Okay, it's not a question, but also an add-on to what you said. I will also say that, or I believe a good understanding of data science will help you to excel in public health, because you can apply some of the principles. Like now, let's say if you are good at predictive analysis, you can which has a basis in data science. So you being good with predictive analysis, you can use that application or skills in public health to predict diseases and tell how, or in the next 10 years, this will be the outlook. And then based on that, based on the findings, then you will advise, policymakers or stakeholders on what to do to prevent the condition or the disease in the next 10 years, so that even if there will be some cases, it will be lesser. Yes, so I think having a good understanding of data science will help you to excel in public health and then epidemiology as well.
Thank you. Is there any other question?
So it should be called biostatistics and data science.
Sorry, can you just repeat that?
All right, Prof. Sorry that I burst in. I said, does that now mean that it should be called biostatistics and data science? Since one will have now, the world is data driven. So I think the two should be inculcated together as they are being taught in public health.
Considered together. I'm not so sure, because public health is, at least the setting in which I work, it is not large, largely data driven to that extent. We are still doing trials and smaller scale studies, and where it is essentially remaining at public health. But I understand the point that was previously made by Kojo, that if you know data science, then you can think of applications of data science in public health. If you have provided, you have the data, the data for prediction modeling and so on. But I think in public health, you a better understanding of the statistical techniques rather than the tools is what is required. But a combination, nothing like a combination of the two. I mean, epidemiology and data science. Yes, that's best. Yes, Kojo, go ahead.
Okay, thank you. So still an add on. If
Yep.
you look at, you look at the domains of data science, we have the knowledge domain. So the knowledge domain could, comprise of so many fields. So if, let's say, you are a public health expert, that will be your knowledge domain. And within that too, there is also, you should have a background in statistics or mathematics. So if you are good with statistics, at least you have some, basic skills or or you should have some basic skills in data science. One, you understand how, as we are even learning today, how a normal distribution should look like. So if you don't have that basics, then that means you can't even do, or even reading public health will be a challenge, because public health, you are dealing with the population and you should know how your population is going to be distributed. So that at the end of the day, if you want to make any decision or any conclusion, it will be based on that. So you having, some background in statistics and then learning further, to have a broader knowledge in the data science will also help. So you learning data science, don't see it to be an off-track kind of thing, but it is also to help you as a public health expert. Okay, so I think that we can consider this one too.
Okay, so if there is no more questions, shall we just take, shall I go to the next session, or do you want a 5 minutes break before I go? Oh, there's one more question. So, oh, okay. Yeah, so is there, Kevin, how do we proceed? Is there a break, or I just proceed to the next one?
Okay, dog.
I think 5 minutes break will do.
Okay. So we'll break for 5 minutes and reassemble. Yeah. Okay, so in this session, we will see about testing of hypothesis and some of the parametric, very basic parametric tests. Again, just giving a flavor of, using biostatistics in clinical and public health. So what do we understand by inferential statistics? When we are trying to draw conclusions about the population from a sample, we call that as inferential statistics. So if we are to estimate the prevalence, can you hear me? Because there's a heavy rain going on. Is it possible to hear me?
Yes, please, we can hear you.
You're audible.
Okay, thank you. Okay, so when we are trying to make an estimate of, say, a disease prevalence or something like that about, in the population based on a sample, we are talking about estimation. But on the other hand, we are trying to compare something between two groups or between two time points, or looking at the association between two particular variables. Then we are doing a testing of hypothesis. So that's what we will see today in this coming session. So an example for estimation is, suppose we are interested in looking at the prevalence of overweight and obesity in urban school-going children, then that is, we are trying to estimate a particular value, but we are not comparing it with against anything. We are just understanding what is the prevalence. The second example is where we may probably do a testing of hypothesis, where we are trying to see the association between maternal pre-pregnancy BMI and birth weight. So let's say there is literature which says that maternal pre-pregnancy BMI is associated with birth weight of the child, and we want to examine that in our setting, then in that study, we will do a testing of hypothesis. So we will see this. So in this session, we will talk about estimation, and there will be an introduction to statistical hypothesis, the errors in testing of hypothesis, the steps involved, and demonstrate the processes in testing of hypothesis through a few parametric tests. That's what we will do today. So when we talk about estimation, we are having a sample statistic. That means something that we would calculate in the sample, but trying to understand what is there in the population, which is the population parameter. So if we are talking about the prevalence of overweight and obesity in the sample, that is a statistic, but we are trying to estimate what that prevalence of overweight obesity is in the population. And then we are talking about estimation. Now, this greatly depends on the sample that we have, how good our estimate is. But let's say we have drawn a good sample, a representative sample, and so on. So then we are trying to understand what the population parameter is. That is the prevalence of overweight obesity in the population. Let's say we were examining everybody in the population, then we will have an exact, correct value for what that prevalence is, and that is our parameter of interest. But we don't do that. We examine it only in a sample and try to estimate it for the population. So let us say we examine this and estimated the prevalence. So this is another example. So the prevalence of anemia among women in reproductive age is 55.3% according to a survey. So we are having an estimate for the population prevalence of anemia as 55.3. But that's one single value. And we know that since we have drawn this inference from a sample value, we are making an estimate based on a sample, there will be an error. It cannot be that in the population, it will be exactly 55.3. It has to be something different. It will be something different. So then we need to understand, okay, how much variable, how much different is it likely to be? And that is why we move away from what is called just a point estimate to what is called an interval estimate. And then we start talking about confidence intervals or uncertainty intervals and so on. So, so if the prevalence of anemia was 53.3 in women in reproductive age group, you would like to understand what is the likelihood of this particular value and what is this value likely to be in the population. So remember that the population value is one, the parameter is just one value. We need to understand how close to that population value we are based on the sample. And the confidence interval will help us to understand that. So what does the confidence interval essentially tell us? It gives us an understanding of how precise our estimate is. For example, look at this. So the prevalence of anemia in preschool children in Asia was estimated to be 47.7% with a confidence interval of 95.2 to 50.3. Now you can see that the confidence interval is quite close to the point estimate that we had. That means I'm quite precise in my estimate of the prevalence of anemia in Asia, which is 47.7. I'm quite close to that. I am having a pretty precise estimate. Look at the second example. The prevalence of anemia in preschool children in Oceania is 28%. But look at the confidence interval. It is quite wide. It is 15.8 to 40. So that is a very wide interval. Now, this tells me that I don't have much confidence. There's a lot of uncertainty in that estimate of 28%. So it could be, this is a less precise estimate as opposed to the earlier one for Asia, which is a much precise estimate. Now, why the difference? This difference essentially comes in because of the sample size that has been estimated, that has been used for this estimate. If the sample size is small, you are likely to get a wider confidence interval, a less precise interval, and therefore you're unsure of your true population prevalence. It could be as low as 15.8 or as high as 40. As opposed to if you have a large sample size, then you are having a precise estimate, and therefore we are more confident about the value that we get. So that is why not only the sample that we draw, that is the representativeness of the sample, but the sample size is also important when we are drawing estimates like this for prevalence and incidence and so on from a population. So let's see here. In a random sample of 705 children aged 8 to 10 representing district, the mean BMI was found to be 15.6 and the 95% confidence interval is 15.4 to 15.6 kilograms per meter square. I should have specified the unit. So here you can see that we are having a very precise estimate with a sample size of 705. That means this sample size is quite sufficient for us to draw quite a precise estimate. And why 95% confidence interval? Remember the normal curve earlier, we said there's something about this 95% being covered within plus or minus 2 SD in a normal distribution. So just keep that in mind, and that is what we are keeping on using that concept. Now, errors, bias can come in. There are various sources of bias while drawing estimate, and that is something that you have to be very, very careful. I don't think we have a session really on sampling and so on, but that is critical in drawing inference. And one of the biases could be because the samples that we have drawn are not representative of the population. So this can arise due to undercoverage. That means some sections of the population was not represented in the sample. This typically happens even when we do large scale surveys. For some reason, some people who are harder to reach or something like that gets misrepresented in a survey, and therefore there is undercoverage of that particular of a particular section, and therefore we get bias. Another reason could be non-response bias. One section of people refuse to respond to the survey, and because of that we have a unrepresentative sample, and the bias arises. So they were reached out, but they refused. Let's say we are doing anemia, and some people have some hesitation to give blood. Let's say it is not, they don't consider it culturally appropriate to give blood for any kind of testing. In that case, we are not getting a sample from that, and they are non-respondents. And another reason could be that some people are voluntarily coming forward for a survey. Let's say I'm doing a survey on overweight, obesity, and people who are doubting that they are overweight, obesity, thinking that maybe they have some benefit in that particular survey, are coming forward and volunteering for the survey, and therefore we have a voluntary response bias. So there are many sources. These are just 3 sources of bias, but what is important, the takeaway message is, when you are drawing inference, it is very important for you to be sure that your sample is representative of the population, particularly when you are drawing prevalence estimates. So if you are going to state that this is a prevalence of a particular condition in a population, you have to be very sure that the sample that you drew is representative of the population for which you are concluding that prevalence to be. So moving on from there, are estimates enough? Is it just enough that we say this is the prevalence or this is the incidence of a particular condition? No, very often we are asking the question, is there a difference? Are there associations? And in which case we come to testing of hypothesis. And in statistics, we state what is called the null hypothesis. The null hypothesis is usually a hypothesis of no difference or no associations in testing of in statistics. So hypothesis is nothing but a theory that is put forward. Now, null hypothesis can be stated otherwise. There are different kinds of, say, clinical trials such as superiority and non-inferiority trials, where we state the null hypothesis slightly differently, but we won't go there today. All we will talk about is a typical case of null hypothesis where we are stating that there is no difference between the groups that are being studied. So the research question is BMI different between urban and peri-urban versus peri-urban and rural children? So one group are urban children, the other group are peri-urban and rural children. And what we are interested in seeing if there is a difference in BMI between the two groups. So essentially, they are two independent groups. Children either belong to the urban or to the rural and peri-urban group. One child cannot be in both the groups at the same time, and therefore they are independent groups. Now, we have the null hypothesis, which is the hypothesis of no difference. But we also have an alternate hypothesis, and the two hypotheses are competing. So when the null hypothesis states that there is no difference, the alternate hypothesis states that there is a difference between the groups. But we always test for the null hypothesis. There is a special consideration for the null hypothesis. The statistical test is always for the null hypothesis, and only if we have sufficient evidence to say that the null hypothesis is wrong, then we go for the alternate hypothesis. So we never test the alternate hypothesis. The testing is always for the null hypothesis. So rejecting the null hypothesis suggests that the alternate hypothesis may be true, and that is the basis of testing a hypothesis. So see this, the difference between urban and rural, the BMI, in the urban it is 15.65 and in the rural it is 15.03, the difference being 0.62 kilograms per meter square. Now, if you ask me, is this different? Doesn't look very different. So maybe not clinically different. So is it due to chance that there is a slight difference in the mean BMI? Now we will have to test this using a statistical test. So then we should understand, okay, we are trying to understand what is there in the population. That is the population BMI in urban versus rural, is it different in the population? We don't know. We are only dealing with a sample. And when we look at the sample, we will be making a decision, and this decision may be right or wrong. So let us consider the first situation where actually there is no difference in the population, and that is the truth. The truth is that the rural and the urban BMIs are the same. So that's the truth. But we don't know that. So we are examining the sample, and then we conclude not to reject the null hypothesis. There is no sufficient evidence to reject the null hypothesis. So the truth is that there is no difference, but we don't know. But we are not rejecting the null hypothesis also based on the data. Therefore, we are making the right decision. So we always want to make the right decision. So this could be the right decision. But sometimes, let us say for some reason, because of a biased sample, we reject the null hypothesis. We examined the data and looked as though there was a big difference in BMI between the two groups. Maybe one group was not represented in the rural area. But for example, let me say some tribal group which were more, low BMI were not represented in the rural population. And therefore, it appears as though they are very different, but in fact, actually they are not different. In this case, we are committing the type 1 error. The type 1 error is when in truth they are the same, but we are concluding by just examining the data that they are different. And that is a type 1 error. Now let's think about the other side. Let's say the two are actually different. The urban children have higher BMI as compared to rural. We are trying to understand that using our sample. We don't know the truth. When we examine the data, it appears as though both the BMIs are the same. So we are making the conclusion not to reject the null hypothesis. In this case, we are committing the type 2 error. So the type 2 error is when we do not reject the null hypothesis, although the null hypothesis is wrong and the alternate hypothesis is the truth. That is, there is a difference. So we don't want to be here as well. So we don't want to be either in type 1 error or type 2 error. We want to be making the right decision. So here, if there is a difference, we want to conclude in the end of the study that there is a difference between the two groups and which is the right decision. So often when we do studies, we want to be in the last box over there. That is, we think there is a difference and we want to be concluding that there is a difference. We don't want to be either in type 1 error or type 2 error. Now, as I said earlier, we are testing for null hypothesis and there is a preference for null hypothesis. The type 1 error is considered more serious. So we will look for maximum evidence to say that the, to conclude that the null hypothesis is not true. So until and unless we have sufficient evidence to reject the null hypothesis, we will not. So for that, we calculate the probability of the type 1 error. Now, the probability of type 1 error is indicated as alpha. This probability has to be minimal. If the probability of wrongly rejecting the null hypothesis is very small, then we can confidently say that there is a difference. By examining the sample, I am able to conclude that there is a difference in the population and that decision is correct. With a certain amount of confidence, I will be able to say. But that probability has to be very low. Now, what is type 2 error probability? It is usually indicated as beta, and that indicates as to the power of the study. That means the ability of the study to detect a difference if the difference is actually there, and that is the power of the study. So we usually use that in sample size calculation. So higher the sample size, higher the power of the data to detect the difference if the difference is actually there. So if the power of the study is low or the sample size is low, then we will get wide confidence interval and we are not so sure about the data. So these are the two errors, and the probability of type 1 error is alpha and the type 2 error is beta, and we try to control for both of them in our sample size calculations, and we kind of keep an arbitrary cutoff of 0.05. I re-emphasize, it is an arbitrary cutoff of 0.05, which has been traditionally accepted as a cutoff of type 1 error. So we say that if the probability of type 1 error is low, sorry. If the probability of type 1 error is low, how low? Lower than 0.05, we conclude that, okay, there is sufficient evidence for us to say that there is a difference between the two groups. So for example, in our study, let us say the p-value or the probability. The p-value is nothing but the probability of the type 1 error. The p-value is 0.2. It means that we do not have sufficient evidence to say that there is a difference between the urban and rural BMI, and therefore we will conclude that there is no difference. But at least we cannot observe sufficient evidence to say that the BMIs between the two groups are different. So the evidence is not there. Whereas when the p-value is less than 0.001, then what are we saying? The probability of type 1 error is very low. Us wrongly rejecting the null hypothesis is very low, and we will conclude that there is a difference between the two groups, the urban and rural PMI. And this is what we are observing from the data, and we are pretty much confident that the difference is there. So the arbitrary cutoff that we use here is 0.05. So the question here, I will answer that straight away. Is there a difference between the p-value and the type 1 error? The p-value is nothing but the probability of the type 1 error. The type 1 error is wrongly rejecting null hypothesis, and we don't want to be wrongly rejecting null hypothesis. What does that mean? The null hypothesis is true. The two groups are the same, but we reject null hypothesis and say that they are different. That is wrongly rejecting null hypothesis. That probability, that error is the type 1 error, and the probability of that error in our sample is what we call as the p-value. So if p-value is less than 0.05, we say that the difference is statistically significant and reject the null hypothesis. If the p is greater than 0.05, we say this statistically not significant and we do not reject the null hypothesis. Now, p greater than 0.05 is not sufficient evidence for us to say that two groups are the same. Now, please note, this is an error that many people make. They think that just because p is greater than 0.05, the two groups are the same. It is not that. It is just that we do not have sufficient evidence to state that the two groups are different. And therefore, we are stating that there's no sufficient evidence to say that the two groups are different. Because you can get a P of 0.0, like greater than 0.05 by just having a very small sample size. So instead of examining or doing the study in 100 people, if you do a study with 10 people, comparing 10 urban BMI versus 10 rural BMI, you can land up with a p-value of let's say 0.08 or 0.1 or so. But that doesn't mean that they are the same. It's just that you are underpowered. You do not have sufficient sample size to examine that difference. And that is the reason we are getting that non-significant finding. So this is an error that many people make. And I would just like you to note that. There are some other questions also coming up. We'll take that up in the end. Okay. So how do we arrive at this p-value? How do we understand what this p-value is and from the sample data that we have? So there are several steps that one has to undertake once they have the data to come to this p-value. So these are, so once first we have to set up the null hypothesis, find the test statistic value, then refer to the distributed value, find the p-value, and conclude. Okay, we'll see that in a couple of examples. So this is a typical formula for a test statistic: observed minus hypothesized divided by standard error of observed. So there are many statistical test statistics, several of them. The way we will choose them is based on some criteria. The first one being, how many groups are we comparing? Now, in our BMA example, we are comparing two groups, rural and urban. Now, are the groups independent or dependent? Is there a, so in our example, they are independent groups. The urban and rural are independent groups. And then the type of data, is it continuous or categorical? So all of these information help us in identifying the right statistic to use. For example, in this case, you can see, so examples for independent or dependent groups: birth weight of boys and girls, they are independent. Boys and girls are independent groups. Antenatal and postnatal BP of group of women, they are dependent. That means it's in the same group of women that we are measuring antenatal and postnatal BP. In match studies, where an individual in one group is matched to the other, they are actually dependent because there is some relationship between them. They are not truly independent. So the test statistic would be different. Now, type of data: birth weight is a continuous data, whereas smoking status is a categorical data. The test statistic that we will use would be different. We will see an example of doing comparing two independent means. So we will stay with the BMI example. And here the null hypothesis is that the samples are from the same population. That means what? The BMI of the rural and urban children are the same. And that is what we are testing essentially. We are testing whether the mean BMI in group 1 is equal to mean BMI in group 2. Now remember, for normal distribution, there are two parameters, mean and standard deviation. So when we are comparing just the mean, if you remember those different colored bell-shaped curves, the two distributions could be different, not only because their means are different, they could be different because their variances are different. Now, you saw three plots where they had the same mean but different variance. Some were flat and some were steep. So if we were to compare two means alone, that means we are assuming that their variances are the same. So that is one of the assumptions of doing a test for two independent means. So let us go into the test. So here is a test statistic, and this test statistic is called the t-test, the student's t-test. And the student t-test here is essentially looking at the difference between the two means. Actually, there is a -0 here, which is just -0. So we are not thinking of that. Divided by the standard error of the difference in means is the test statistic. Now if you do all that calculation, you will get a t-value of 2.46. And corresponding to that t-value of 2.46, you get a p-value. That means the probability of your type 1 error. The probability of type 1 error in this case is 0.014. And this means that the probability of us wrongly rejecting the null hypothesis is very low as 0.014. And therefore, we conclude that there is a difference in the BMI between the urban and rural groups. So, and the observed difference here is 0.62 with a confidence interval of 0.13 to 1.11. Now, what is this confidence interval telling us? The point estimate of difference between rural and urban is 0.62. The confidence interval is not including 0. So since we have both the lower limit and the upper limit of the confidence interval to be positive, we are concluding that they are different. And that is what the p-value is also telling us, that the two groups are different in BMI. Therefore, we conclude that BMI in urban and rural populations are significantly different. And in fact, the urban BMI is higher than the rural. So that is our conclusion. So let's stay with that. Okay. So this is test of two independent groups. Now, the next question that we have is test of paired means. So test of paired means here they are not independent. So we are still looking at mean, but the means are not independent. So this can be an example when we have pre-post observations. We are measuring the same thing in one group of individuals before and after, let's say an intervention. So if we are looking at weight before and after a dietary intervention, then we are talking about paired sample t-tests. So you see this t value, is computed in a slightly different way. This is a paired sample t-test. And here we see that the paired sample t-test value is 11.94 and the corresponding p-value is less than 0.001. Again, it is telling us that there is a difference in the okay, what is this? This is energy intake. Okay, it is not weight, but it's energy intake. That's why it's such a high value. So what is the difference? It is significant at less than 0.001. There is very low probability that this difference is occurring due to chance, and therefore the pre and post intakes are statistically significantly different. So this is the paired t-test, because although we are comparing means, in this case, the observations were made in one single group, not independent groups, one single group before and after intervention. Now, suppose we have more than two independent groups. In this case, we have to use another test and not multiple t-tests. So doing multiple t-tests will bring about the problem of multiple comparisons, and that increases our type 1 error. And therefore, we have to do one single test instead of doing 3 different tests. So let's see this example. So if we are comparing the BMI between 3 groups of people who are based on the TV viewing duration. So people who view TV for less than 45 minutes, 45 to 90 minutes, and more than 90 minutes. And these are children. And we are looking at the BMI. So let us say the question is BMI related to duration of TV viewing? And we have chosen to split the TV viewing into 3 categories. So what are we comparing? We're comparing the mean BMI of children in these 3 groups. That is less than 45 minutes, 45 to 90 minutes, and more than 90 minutes. So they are independent groups. A child can be in only one of these categories. They are independent groups, and we're comparing the means between the 3 independent groups. Now, this is what is called an analysis of variance. And the test statistic here is what is an F-test. Earlier, we were seeing the t-test, the independent sample t-test, and the paired sample t-test. In this case, it is an F-test, which is a ratio of the between group variance to the within group variance. Okay. So what we get out of an analysis of variance is an analysis of variance table, an ANOVA table. So you see here the mean BMI in group 1 is 1.63. Now these are standardized BMIs, okay? Because in children, it is depending on their age and sex, the values have to be standardized. So standardized BMI is 1.63 with an SD of 0.63. In group 2, the standardized BMI is 1.65 with an SD of 0.7. And in group 3, it is 1.86 with an SD of 0.6. Now the question is, are these different? So what are we getting? Corresponding to the F statistic, the p-value is less than 0.001. Cannot see that. Yes, less than 0.001. And therefore, we conclude that, yes, there is a difference between the three groups in BMI of the children. Okay. And so then we ask the question, okay, we started off saying the null hypothesis, the BMIs are the same. Mean 1 is equal to mean 2 is equal to mean 3. The mean BMI is the same between the three groups. And after doing the statistical analysis, we conclude that the BMIs are different between the three groups. But the next thing that we would want to know is which among these three groups are different. So here we can think of how many pairs of comparison? 3 pairs of comparison, group 1 versus 2, group 2 versus 3, and group 1 versus 3. And to have an understanding of that, we do what is called a post hoc test. So a post hoc test. So a post hoc test in this case, a Bonferroni adjusted test, will tell us which two groups are different. So it is not right for us to do an independent sample t-test for paired comparisons between two groups. It would not be correct. So we are doing a post hoc test. There are many post hoc tests available based on the nature of data and the number of comparisons that you are doing. You can choose to pick. So see here. So group 1 versus group 3 is significant. Group 2 versus group 3 is significant because both of these p-values are less than 0.05. But group 1 versus 3 is not significant. And you can obviously see that there's hardly any difference in the means between the two groups. So our overall test is telling us there is a difference between the three groups, and our post hoc test is clearly showing us which of the pairs of comparisons are different. So the lowest, so the group with the highest amount of TV viewing has significantly higher BMI as compared to the other two groups, as compared to the first group, as well as compared to the second group. But there's no difference in BMI between the group 1 and group 2. So that is our conclusion. So that is a post hoc test that you can do after doing an analysis of variance. In some cases, when you do an ANOVA, you will get a p-value of, let us say, 0.045. And when you do your post hoc test, you might not get any of the pairs to be significant. So what you have to do is to actually report the data as it is. You have to say that the ANOVA gave this, but the post hoc test clearly does not give any pair to be statistically significant. This happens when the data, the p-value is very close to 0.05. So this brings about the question, how valid is this cutoff of 0.05? So it is very important for you to understand that 0.05 is just an arbitrary cutoff. It is just an indicative value that people find convenient to compare against. So you can have other cutoffs also. That is fine as long as you can justify a 0.045 p-value against a 0.051 p-value is not very different. It is not telling us much. It just merely says that the probability of type 1 error was slightly higher when you are saying 0.051. So it is very important to report your data, summarize the data, give the mean, give the standard deviation, and state exactly the analysis that you did, and say that your p is equal to 0.051, and not let people come back and tell you that no, that is not significant. No, all you have to say is that p is just an indicator. It is just you're comparing it against an arbitrary value. So it is very important for you to report the 95% confidence interval, which will give you a clearer understanding of how different your two groups are rather than just the p-value. There has been, unfortunately, in the past, a great emphasis on the p-value, and publication really depended on whether you got a p less than 0.045 and not. But things are changing, and the statistical reviewers these days, we people are looking more for, looking at the confidence interval and trying to understand the data. Another point I wanted to make here is about, especially for people who are from public health, is to not have so much emphasis on the statistical significance. What is important more in public health as well as clinical sciences is to look at the clinically significant difference. So for example, in the previous comparison, we saw that the difference in BMI was only 0.62, although that was statistically significant. Now, if you think about BMI, that is a minute difference. So it may not be clinically significant to really launch a new intervention or anything like that, but it is statistically significant because you happen to have a sufficient sample size to examine that difference. So it is not all about statistics. You have to combine different information to draw any conclusion in any study. So that is the end of my slides. So let me just have a quick look at the questions, and then I will look at the questions. Why do we have different p-values for group 1 versus, okay. Let me just go. So yeah, this is where. Is there any difference between p-value and type 1 error? I answered that. Comment on clinical significance. Yeah, I already commented on that. It is very important to look at clinical significance, especially with respect to that BMI example. And BMI of 0.062, how different is that BMI? Not much, although it is statistically significant. Can you see this? So that is a BMI difference of 0.62, not very different, although it is statistically significant. So it is very, very important to pay attention to the clinical significance. Sometimes your p-value will not be less than 0.05. It might be 0.06, but it is still important for you to say that, yes, I observed a clinically significant difference. Let's say the BMI was different by 2 units. It is important for you to say, yes, my difference was, the observed was 2 units, although it was not statistically significant. It is just calling for some more research in that area. You are not able to draw a conclusion there. So there's a need for more research in there. When is it useful to use post-hoc tests in ANOVA? Always in ANOVA, when you get a statistically significant difference, immediately the question comes, which 2 groups are different? So you may be comparing 3 groups or 4 groups. And as the number of groups that you have increases, the paired comparisons also increase. And you're always asking the question, is group 1 different from group 2 or group 2 different from, if group 1 different from group 3 or group 2 different from group 3? These questions you are asking. So you have to do a ANOVA, a post-hoc test after ANOVA. But if the ANOVA was not significant in the first place, let's say the p-value corresponding to ANOVA was 0.8, there's no point in doing a post-hoc test. So that is the thing. We are unlikely to get anything significant in a post-hoc test as well. So if you get a statistically significant finding in your ANOVA, or you get something that is close to statistical significance, it is worthwhile to do a post-hoc test. Why do we have different p-values for group 1 versus group 3? So let me just put that. So this is group 1 versus group 3. This is mean of group 1 versus mean of group 3. That comparison, the p-value, the difference p-value is 0.025. You can see that there's 1.63 versus 1.86. For that difference, the p-value is 0.25. For 1.65 versus 1.86, the p-value is 0.04. And the SDs are also different. So all that plays in. That is why we are having different p-values. Whereas if you're looking at group 1 versus group 2, there's hardly any difference. And therefore, the p-value is not anywhere close to 0.05. It's 0.76. I hope I answered your question. Then the next question is, I think the first one is for group 1 versus group 2. Oh, am I? No, this is correct. Group 1 versus group 3, group 2 versus group 3, both of them are significant. This versus this is significant, this versus this is significant. but there's no difference between group 1 and group 2.
Sorry, ma'am.
Sorry?
Yes, sorry, I was just confused because you have group 1 versus group 3. It's repeated, so I was just confused.
Oh,
I thought maybe-
oh, no, that's mistake. It is group 1 versus group 2. I'm so sorry. Yes, that's group 2. Thank you for pointing out. I didn't see that mistake. Okay. So is it statistically correct to say there is no obvious difference between the two groups without a stat test? No, it will not be, because you will have to qualify it with a statistical test, because you don't know whether the observation that you had is due to chance or not. So you can just say that, this is the mean that you got in group 1. This is the mean that you got in group 2, but you cannot conclude anything about them. So what does obvious mean? So vague terms will not work. You will have to qualify it with statistics. Yeah, I think that's all. So, any more questions? Any question? Okay, thank you all for your questions on the chat. If there's any more question, I can take that, and then it's 8:22. Yeah, and then we can take another maybe, how many minutes break, Kelvin? Now we have 2 more sessions to go. Kelvin?
I think 10 minutes would do.
10 minutes?
Yeah.
Okay. Okay, so we take 10 minutes break here, and we will go back to the 3rd session. Thank you very much. So this session will be on non-parametric tests. Let me share the slides. So the statistical tests that we saw in the previous session was all parametric tests. That means they dealt with statistics that used either mean or standard deviation in the calculation. Both means and standard deviations in the calculation. But so they are called parametric tests. So there is an inherent assumption for those tests that the data should follow normal distribution, so that representing the data as mean and standard deviation is appropriate. But what if the data does not follow normal distribution, or the data is not symmetric? Then what is to be done is what we will see now. And in this session, we will also have a quick look at correlation and a regression. So this is distribution of income, and you can see that it is positively skewed. It is not symmetric about the mean. And in this case, doing an analysis of like a t-test would not be appropriate. So what do we do? So very often we deal with such kind of data, and then we have to resolve to tests that, or calculations that do not use parameters, and they are called non-parametric tests. They are simpler to calculate. Like for example, a median is much simpler to calculate than a mean, or an interquartile range is much simpler to calculate than a SD. But there are some disadvantages also. So non-parametric tests are based on ranks, basically. So you arrange the data and order them in terms of ranks. So you have to be able to have the data as the data has to be ordinal at least. So you have to be able to arrange the data in a particular order, either in descending or ascending order, to use non-parametric tests. They are less influenced by measurement errors or by outliers rather than the parametric methods, because the parametric methods are dependent on mean. And if you have outliers in the data, the mean is influenced by the outliers. So for example, if you have a very high value, let's say 2 very high values, your mean tends to shift to the higher side, and therefore the test is influenced. So that is why when you have some outliers, it might be good to use a non-parametric test. Sometimes when you have some kind of measurement error, then because the non-parametric method is solely dependent on the rank and not the actual data per se, and therefore it is less influenced by some measurement error in the data. Sometimes you will have data that are below assay values. So you would have say, if you have worked with lab-based data, sometimes labs cannot detect some values which are very, very low. So they will only give that if the lab limit of detection is say 2. It will just give, the lab data will say that this particular subject has a value less than 2, and you don't know the exact value. In such cases also we can use non-parametric tests because we don't know the exact value. So in another example where you can use non-parametric tests is when a sizable fraction of the data is actually 0. You have a lot of zeros in your data. For example, in a population like ours, when we are doing diet recalls, if you ask the quantity of fish consumed, there will be a large proportion of our sample which would report zero consumption. So in such kind of data also non-parametric methods can be applied. So as long as you can order the data, you can apply non-parametric tests. So here is an example. So these are the original scores. You arrange them in ascending order and then rank them. So very often when you are dealing with larger numbers, you will have ties in the data. That means 2 or more observations having the same value, in which case your rank is an average rank. I won't go into the details, but sometimes non-parametric tests can get influenced by too many ties also. So please be aware of that. So the Mann-Whitney U-test so you can ask the same kind of questions as you are asking in parametric tests using non-parametric tests also. For example, if you want to compare something between 2 independent groups, you can do a non-parametric test, just like how you used a independent sample t-test. So let us say we are looking at some score and you want to compare the score between 2 groups. Then we can use the non-parametric test, which is a Mann-Whitney U-test. So essentially what are we doing? We are arranging the data in ascending order. Then we are ranking them, and then we use the sum of ranks. And that is essentially used in a test statistic calculation. So that is the process. So let's see this example. So the null hypothesis says that there's no difference in median GHQ score. So this is a health score between 2 groups. And since there are 2 independent groups, we can use a Mann-Whitney U-test. And the alternate hypothesis says that there is a difference between the 2 scores, 2 groups. So the U calculation, which is a test statistic in this case, is done based on the ranks, and you get a value. You get a corresponding p-value, which is telling you that the difference that is there between the 2 groups for GHQ score is statistically significant because the probability of type 1 error is very small. How small? It is less than even 0.01. So we reject the null hypothesis and state that there is a difference between the 2 groups. So that is the Mann-Whitney U-test, same as the independent sample t-test. It's just that we are not calculating mean and SD and so on. We are not using the t statistic. We are using the U statistic in this case. Now, suppose you have 2 dependent samples or 2 paired samples, just as how we used paired sample t-test. An alternate is there in non-parametric setting as well, which is the Wilcoxon sign rank test for paired data. So in this case, we are comparing the data before and after, let us say, an intervention, but let's say we cannot use the parametric test, and therefore we are using non-parametric tests. So the null hypothesis would be that there is no difference in the data between the 2 time points, and the alternate hypothesis states that there is a difference between for the data between the 2 time points. So it is one single group. So this is an example. One single group of individuals pre-training weights and post-training weights. So this is the data. Essentially, you have to calculate the difference between the weights and then rank order those differences. And that is how this test statistic works. And in this case, you get test statistic value and a p-value corresponding to that. And here the p-value is, where is the p-value? Okay, the p-value is greater than 0.05, and therefore we say that yes, the p-value is 0.375, and therefore we say that there is no difference between the two time points. The weights between the two time points are comparable. We do not have sufficient evidence to say that the post-training weights and the pre-training weights are different. So this is an example of paired data where we use non-parametric tests, and the non-parametric test in this case is the Wilcoxon sign rank test, because you are looking at the difference between the pairs of data. That means every individual's before after data, the difference between them, and ranking them. So you can see that the non-parametric tests computationally are much easier, and you don't have the extra stress of confirming whether the data follows normal distribution and so on. Because even if the data does not follow normal distribution, it is fine. You can go ahead and use the non-parametric test. You can use them in situations where you have outliers, or you have skewed data, or you have mismeasured data, or when you have data within below detection limits. In any of these situations, non-parametric methods seem to be appropriate. So why don't we use them always? So there are these are the advantages of non-parametric tests. So it is simpler in calculation, and the inference is based on rank. So the problems that exist with parametric methods does not exist here. But the disadvantage is that it tends to waste information, because we are actually collecting this quantitative data, because it is not, but it's not fully utilized in a non-parametric test. Because, for example, if you look at the weight difference between the pre and post, you're only looking at the rank of the difference. You're not looking at the magnitude of the difference. So you are, in fact, wasting information. And that is the biggest drawback of non-parametric tests. You're not fully utilizing the data that you have. And therefore, it is not as efficient as parametric tests. So sometimes you may need a slightly larger sample size if you plan to do non-parametric tests as opposed to parametric tests. So these are the disadvantages of using non-parametric tests. So let me repeat, we can use non-parametric tests where the assumptions of normality or the assumptions of parametric tests are not met. That is, if you have skewed data and so on, it is appropriate to use non-parametric tests, although there are some small disadvantages to these non-parametric tests. Another thing is, alternates to non-parametric tests are not that many. So we don't use them as much as as the parametric test. So this is a table which shows each parametric and the corresponding non-parametric tests. So now this is this data. Okay, this we saw earlier. I won't do that. Okay. So we'll quickly go to the next test, which is the chi-square test. So the chi-square test is a test of association between two variables, but the association is slightly different. All this while we were talking about data which is continuous in nature. But what if we are dealing with two categorical data? For example, in this case, we have two variables, which is the sex of the individual and the overweight status. And we are interested in seeing whether there is an association between overweight status and the sex of the individual. And when we are examining this kind of an association, we do what is called a chi-square test. Now, for doing chi-square tests, it needn't be necessarily 2x2 tables. You can have tables with many more categories. You can compare a 5 by 4 table. That means there are 5 rows and 4 columns. You can do a 2 by 10, doesn't matter. But it's just that you should have sufficient sample size in each of those cells. And what often happens is when you cut them into too many categories, the sample size in each cell reduces. And that is a problem for chi-square test. So you have to be cautious about that. But otherwise, chi-square test is fine. So here, the null hypothesis is that the overweight status and sex of the child are independent. What does that mean? They are not associated with each other. And that is what we are going to examine using the data. So what does the data say? 8% overweight in male and 7% overweight in female. It looks as though there's no difference. And we have to apply the statistical test. And here, the chi-square value is 0.13. And corresponding to that, the p-value is 0.715. So you see here, just like how our general test statistic was, that is observed minus expected. Here again, we have observed minus expected. The expected values are calculated using the observed data over here. And we conclude that since the p-value is 0.715, we conclude that there is no significant association between sex and overweight obesity status. That means we do not have sufficient evidence to state that there is a difference between, so there is an association between the overweight obesity status and sex of the child. Therefore, we are going with the null hypothesis. That is not rejecting the null hypothesis, and that is our conclusion. So there's no association. Our null hypothesis was that there is no association, and the alternate hypothesis was that there is an association. So we are going with the null hypothesis since the p-value is very large, 0.715. So suppose, so that is test of association when the data is categorical in nature. Now, what if we have continuous data? When both the variables of interest are continuous in nature, then we can do correlation. So, for example, the association between height and weight, or the association between body weight and percent fat, the association between maternal weight and fetal weight, association between blood pressure and age. So here, essentially, we are talking about one single group of individuals in whom multiple measurements are taken. So one group of individuals in whom heights and weights are measured. One group of individuals in whom body weight and percent fat are measured. One pair of mothers and babies in whom maternal weight and fetal weight are measured. Another set of individuals in whom blood pressure and age are measured. So essentially one group in whom these two variables, two different things are measured, and we are interested in seeing whether they are related to each other. And since the variables are continuous in nature, we are going to do a correlation. If they were categorical in nature, we would have done a chi-square test. But correlation is slightly more informative than a chi-square test, because the correlation also tells us the direction of the relationship between the two variables and also the strength of association between the two variables. So the best way, or the primary way by which you should examine correlation, is by using a scatter plot. A scatter plot is nothing but plotting the data with one variable on the x-axis and the other on the y-axis. You get a good understanding of the kind of relationship between the two variables, whether it is increasing or decreasing. What is the pattern of that relationship is a scatter plot. You also have an understanding of whether there are outliers in the data. So essentially, before you do any kind of correlation analysis, you should certainly look at the scatter plot, because these correlation coefficients that we are going to discuss today are examining only linear relationship between the two variables. Suppose the data is not linearly related. That means, let us say that, for example, I know that this relationship exists with respect to hemoglobin of the mother and birth weight of the baby. So the birth weight of the baby will increase along with hemoglobin up to a certain point, And after that, as the hemoglobin increases, actually the birth weight of the baby decreases. So that is not a linear relationship. It is not increasing along with hemoglobin. So it is some kind of a U-shaped relationship. In such things, we should not be doing correlation. But if we don't know upfront what is the nature of that relationship, we might wrongly use Pearson's correlation also. So it is very important to do the scatter plot and understand if there are segments of the data. Is it all one data? So there are so many things that you can observe from a scatter plot. So after you do the scatter plot, to have quantitative measurements, you do a correlation coefficient. So the correlation coefficient is a standard value and it ranges from -1 to +1. And the sign indicating the direction of the relationship and the value indicating the strength of the association. So the closer the correlation coefficient is to 1, the stronger the association. The closer it is to 0, the weaker the association. And a positive value says it is a positive association, that is, as one value is increasing, the other is also increasing. A negative correlation coefficient says that it is, as one value is increasing, the other is in fact decreasing. So all of this you can observe by a scatter plot, but you can't really quantify. So the sign of the coefficient tells us the direction of the relationship, and the numerical part of the coefficient indicates the magnitude of the correlation. So you can also do a statistical test on the correlation coefficient to see whether that is statistically significant or not. So there is a test statistic also for correlation. Now you see here, among the 4 correlation coefficients, which is the larger, which is the strongest correlation? So -0.8 is the strongest correlation. Although numerically you would think that -0.8 is the lowest value, remember the sign is only indicative of the direction of the relationship and not really related to that particular quantity. Okay, so it is a negative correlation, and 0.8 is the strongest correlation out here, and therefore -0.8 is the strongest correlation coefficient. So these are some plots of correlation. The first scatter plots, the first is a positive, then second is a negative, and this is no correlation. Now, moving on, we have seen what correlation is. Now, correlation is only describing the relationship between two variables, association between two continuous variables, but there's no causality assigned there. You can interchange the variables between X and Y, it doesn't matter. It will still give you the same correlation. Same is the case with chi-square, the row and the column. You can interchange the variables, no problem. You will still get the same chi-square value. But if you are examining causality in a study, so let's say in the study design, you are, you have designed in such a way that you can examine causality, and you want to confirm it using a statistical test, then you have to do something further than correlation, and that is regression. And in this session, I would just start off with linear regression. You have a much detailed session later on regression techniques, so I won't go there. And regression is a much used statistic. Even correlation is very much used in data science. So, so I will just give a very brief introduction to linear regression. Okay. So in linear regression, we are trying to look at the dependence of one variable on the other. That is why we are trying to examine causality in regression. So one variable is dependent on one or more variable. So since we are saying that one variable is dependent, we are examining one-way causality. We cannot inverse that. So for example, if we say that the birth weight is dependent on maternal pre-pregnancy weight, that is one-way causality. We cannot inverse it and say that maternal pre-pregnancy weight is dependent on birth weight. No, by logic, by principle, it is a one-way causality, and that is what we examine in a regression technique. So if you were to apply linear regression, the dependent variable has to be continuous, but the predictor or the independent variables can be either continuous or categorical, and you can still do a linear regression. So here is an example. So again, the scatter plot, I would reiterate that you should look at a scatter plot before you do a linear regression or a correlation. Okay. So this is a scatter plot. Looks like there is some kind of association between the two variables X and Y. And as it is a positive association, but we would really like to quantify how much Y would change for unit change in X. And that is what we are doing in linear regression. Let me just pause and have a quick look at the questions. Oh, somebody's asking for a break. I'll just finish this and ask for a break. Yeah. Okay, I'll answer the questions at the end. So here, what we are trying to do is to draw a line through that dots to demonstrate, to show that there is a linear association. Now that there are certain qualities of that line should be the best fitting line. So even if we are doing, say, data science, and you are trying to do all that, different plotting, essentially what we are trying to do is to draw the best fit lines. So in this case, the best fit line is decided upon by a set of criteria. So one is setting the intercept, that is the point at which the line crosses the y-axis, and that is the intercept. And so you can think of it like that. We are moving the line up and down so that we identify the best point at which the distance from observed value to the line is minimal. And that is called, in this case, the residuals, the distance, the difference from observed data to the line. So if you are keeping on shifting this line up and down, at what point do we have the minimal difference between the observed points and the line? That is the intercept value. Now, once you fix that, you have the slope. Which way should the line be? What should be the slope of that line? You can see that there are different slopes here. At what slope do you again have a best fitting line? That means the difference between the observed data and the point on the line. So that is a minimal residual. So in linear regression, our effort is to minimize the residuals. Residual is the difference between the observed data and the corresponding value on the line. So this residual has to be minimal. And the best fit minimizes the sum of squared errors. Error, in this case, the residuals between the observed and the model predicted y values. That is these green dots. So that is what linear regression does. So here you can see the formulae for the regression coefficient, and you can see that correlation coefficient is a part of that formula. So what do we look at when we do linear regression? As I mentioned, now we estimate the regression coefficient. That is the most important estimate when we do regression. You also, in addition, get some idea about the model fit, whether the regression that we are doing is a good regression for the particular data that you have, and a statistical significance for the regression coefficient. So let us see an example of 100 women data whose pre-pregnancy weights and birth weight of the baby are known. So this is the data set that we have. And from this, we know that birth weight of the baby is the dependent variable and the pre-pregnancy weight is the independent variable. Now, we are asking the question, are the two related? And since we can identify a dependent variable here, we can do linear regression. And another criteria was that the dependent variable has to be continuous. In this case, birth weight is a continuous variable, and therefore it is fine. But there are other assumptions. I'm not going to that. So I'll come to that later. So for now, let us say we are asking the question, if the two are related. We can even ask the question. So earlier somebody was mentioning about prediction models. So regressions are greatly used in prediction models. So we can, once we know this regression line, we can even predict what the birth weight of the baby would be if we know the maternal pre-pregnancy weight. Because it would just mean that we are plotting another data point on that line that we have. So two kinds of questions. Is birth weight dependent on maternal weight? The second question is, can we predict the weight of the baby by knowing the maternal pre-pregnancy weight? Both of these can be answered by doing this linear regression. So let's say we did this linear regression and we are getting an R squared value here. So that is one thing that we can look at. In this case, it tells you how much of the variability in birth weight is explained by maternal pre-pregnancy weight. Now, what do you mean by that? Birth weight is variable for every baby. Every baby is having a different birth weight, and therefore they are variable. But what percentage of that total variability is explained by maternal pre-pregnancy weight? Now, if you think about it, 0.123, that is 12.3% is not a big deal. Only 12% of the variability is explained by maternal weight. But you think that it is just one variable that is explaining 12% of variability, which means that this one variable is very important, which is pre-pregnancy weight of the mother. So let's understand what the regression coefficient of this variable is, that is maternal weight, is 16.36. That means for every 1 kilogram increase in maternal weight, the birth weight of the baby would be higher on average by 16.36 grams. So what does that mean? If we have two women who are weighing 1 kilogram different at pre-pregnancy, then the birth weight is likely to be different by 16.36. Remember, this is an average value because there is error. You remember there is always a residual from the observed data to the line. So this is just an average difference. But now we get an idea of how much birth weight can vary by maternal weight. So you see, it is more information than correlation. We are saying that. So by looking at the p-value, in this case, it is actually p less than 0.001. So in this case, we know that it is statistically significant. So there is an association between maternal weight and birth weight. The second thing that we notice, the direction is positive. That means as the maternal weight is increasing, the birth weight is increasing. And the third point, we also know that the birth weight can increase by approximately 16 grams. It's on average 16 grams for every kilogram increase in maternal weight. And you look at the confidence interval. Oops, what happened to my screen? Let me share it again. That was the last slide, so I had yeah. So we also know that. So now if you see this, we can make a prediction about the birth weight. We can see that, okay, for a woman who weighs, let's say 50 kilograms, we can kind of calculate what the birth weight of the baby would be. Although we know that there is possibility of variation, there's possibility of some kind of error, but approximately we can calculate. So we can make predictions. You look at the confidence interval, it is quite tight about this estimated point estimate value of 16 grams. So that is another additional information. So if you are reporting that, it is also good to report the confidence interval. Say that the observed difference was 16.36 with a 95% confidence interval of 7.6 to 25.1. So that is linear regression, but you have to be very careful while making predictions because you have to be always cautious. So suppose you are using a prediction equation that somebody else had developed. You have to be aware under what situation was the prediction equation developed. Let us say I'm having a prediction equation for birth weight versus maternal weight, which I developed in mothers who were weighing between 40 kilograms to, let's say, 70 kilograms. The mothers were weighing between 40 and 70. I cannot use this equation to predict the birth weight of for a mother who is weighing 100 kilograms because I'm then extrapolating the equation, which is not permissible. It may not be right. Maybe beyond 70 kilograms, it is no more linear. So I have to be careful about that. So be aware that it is not just about using equations for predictions. You have to understand the premise or the background from which the equation was drawn. I'll stop here with the presentation and just have a look at the questions. So there's just a second, let me just get my presentation up. Okay, I'll go from bottom. What is the difference between R square and adjusted R square? Okay, so when you are doing multiple regression, that means you have several variables that you are including in the regression as independent variables, then it is useful to look at adjusted R square, because that is adjusting for the number of variables that you have included. In my case, in the example that I showed, there was only one independent variable. So that is simply a R square. So when you are doing multiple regression, it is better to look at the adjusted R square, because there the number of variables is also taken into consideration. Now, on time to event outcome, regression, survival analysis of set. Please comment on eta statistics. Okay. Do you really use eta in your linear regression? Not really. I'm just trying to think of a context in which we use eta. Maybe somebody can help me here. Just trying to think of an example where we would use. Okay, I'll come back to you on that. Time to event outcome. Okay, so in time to event outcome, we can do regression based analysis. So usually we do what is called survival analysis. That is where the outcome of interest is not whether the outcome happened or not. We are also interested in when the outcome happens. So if suppose we are looking at mortality, and we are not just interested whether the mortality happened or not in that sample, we are also interested at the time at which the mortality happened, and therefore the mortality percentage at each time is what is considered. In that, we use regression-based techniques such as the Cox proportion hazard model or other parametric models. We don't have time to really go deep into that, so I will leave that there. But yes, regression methods are there in time to event analysis as well. Can we measure correlation between a continuous variable and a categorical variable? Yes, there are correlation coefficients for continuous versus categorical. Like the name is just skipping my mind. I can't just quickly recall the name of that particular correlation coefficient, but yes, there are correlation coefficients for continuous versus categorical. But if you have non-normal data, continuous but non-normal data, you can do what is called a Spearman's rank correlation coefficient, which is based on rank data. Yes, there's a question, a hand raised. Please go ahead and ask the question.
Okay, Prof. Thank you so much. Can you hear me?
Yes, I can hear you.
Sorry, I just wanted to ask, when you are doing a linear regression and you have a lot of predictors, maybe up to 5, I see a must that each of the predictors, especially when they are continuous, that's quantitative predictors, they must have an association with the outcome. And then, how do you also handle the categorical predictors? Like, let's say sex, let's say HIV status, smoking status. So how do you interpret them?
Okay, that's a good question. So let us say we will stick to the birth weight example, and you want to compare, let's say, birth weight between by status of HIV. So essentially what the regression coefficient tells us is the average difference in birth weight between the HIV positive and the HIV negative. So we use them similar to how it is in a continuous setting. If it is binary, if your predictor is categorical and binary, that means there are only two values. The prediction, the interpretation is easier. That means we can just say positive versus negative, this is the average difference. But suppose if the categorical variable has multiple categories, let us say 4 categories, so 4 categories, then the interpretation or the analysis is not that straightforward. In most statistical softwares, you will have to specify, tell the software that this is actually a categorical variable, and I want the comparisons with respect to one particular category. So let me take the example of anemia among mother, okay, and the birth weight of the baby. So I have a reference category of no anemia, and then I have the comparison, other categories of mild anemia, severe anemia, moderate anemia, and severe anemia. And I'm interested in looking at the comparisons of all of these 3 severities of anemia versus no anemia. Then I have to tell the software that this is the way I have to have the regression coefficients, which is essentially the difference in the average birth weight between the no anemia category and the mild anemia category, the no anemia category and the moderate anemia category, no anemia category and the severe anemia category. So I have to specify the way in which I want that analysis to be done. Otherwise, it is considered as though it is a continuous variable, and that interpretation may not be correct. Did I answer your question?
Yes, Prof. Thank you so much.
There are 2 more questions. When do you do polynomial regression and spline analysis? Okay, so polynomial, so what we saw here is linear regression. Now, suppose that association is not even a straight line. You saw the scatter plot. It was quite clear that you can fit a straight line, but sometimes it is not that. And it is, let us say, a quadratic association. And in that case, we use polynomial regression. And polynomial regression, essentially, we are taking that the independent variables, all the predictors, a little further. Let's say quadratic equation. Then we are having a linear term and a quadratic term. That is a square term. So that is polynomial. So by looking at the scatter plot, we should be able to understand the pattern of the association, and then which polynomial will actually fit the data. Is it a quadratic? Is it a cubic? So depending on that, we do the polynomial regression. Now, splines is really splitting them even further. Spline is more like a data-driven technique, because there we are saying that, okay, fitter regression fits the data. So if, let's say, your curve is going like, in some kind of pattern, it's not at all linear. We are telling that, okay, every now and then you can re-estimate your regression coefficients. So that is spline. We specify the knots. Knots are the points at which the lines can break. So we are letting the data fit, letting the regression fits the data in a better manner when it's clearly not linear, and we don't know how to specify that particular association. We know that it is not quadratic. We know it is not cubic. Then we are saying the data, okay, you now fit based on the way you see it. All we give is we give some specifications about the knots at which the spline has to be fitted. So that is more of a, it's using regression, but it's more of a data-driven technique. So that again, going back to our earlier discussion about data-driven versus, typical public health analysis. From where can we learn to interpret the data? Is there any resource? So generally, when we statisticians analyze data, it is always along with a person who is a subject expert, who has an understanding of the biology that we are exploring. So it is not just about the numbers that we see. There is a basis by why certain associations happen. And in public health, if you are analysts, you have to work alongside them so that you have a better understanding. So it really depends on the area in which you work. So I cannot say that there is, but if it is simply about interpretation of regression coefficients, if you look at any standard regression textbooks, you will be able to understand. So there is a textbook by Lemichaud that we all refer to, or we have given some textbook references in the course outline. You can look at that. So that is one way. But otherwise, with reference to the area in which you are working, you have to work with an expert in that area. How can I handle regression model with 3 or 4 categorical variables with different sample sizes? Let's say a categorical variable for breast cancer risk with high risk, N is equal to 1000, moderate risk 60, and low risk of 10. That is okay. So you are saying that you have one categorical variable. It's not 3 or 4 categories. It's just one categorical variable with 3 categories, and each of those categories having different sample sizes. Now, this usually is not a problem with different sample sizes. You do not have a problem. You can use the regression just the way as with any other analysis. But if you have very small sample sizes, say 10 is actually a little small. The problem that you will have is that your estimate may not be precise. So for your comparison of the low risk versus high risk, maybe you get a very wide confidence interval. So that is the problem there. It is not that you cannot use it. So your confidence interval will be wide. So this N is equal to 10 may be insufficient for that particular analysis. And sometimes in such cases, what we do is to combine categories. So we will choose to combine moderate with low risk and compare both of them against high risk, in which case we will have sufficient number of samples in each category. So we should always be clear that one rule of thumb is that the sample size should be at least 5 times the number of estimates that we are making. So here in this case, if you are having 3 estimates, at least 5 times that, but it's just a rough rule of thumb. Bigger the sample size, it's better. In this case, 100 versus 60 versus 10, I do not think you will really have a problem, but keep an eye on the confidence interval. Why is regression model prediction not suitable outside the range of data it is derived from? Okay, so that is because I wish I could draw here. So we will go back to the example of birth weight versus maternal pre-pregnancy weight. I said that the equation was drawn from a sample which had pre-pregnancy weight ranging from 40 to 70. And in that range of maternal weight, I am seeing that it is a linear relationship. But beyond that, beyond 70 kilos of maternal weight, maybe it is not even linear. After that, it flattens because the birth weight of the baby cannot go on increasing according to mother's weight. The mother's weight can go up to say 150 kilograms, but the baby's weight cannot increase linearly like that. So at some point, maybe it may flatten. So as us assuming that it is linear, even beyond the point that we have examined the data will be incorrect. So that is just an assumption and we cannot go by that. That is why it is not right to extrapolate. If we are making predictions for data within that range, we are perfectly fine, but outside we may not be correct. So be cautious. So for non-normally distributed data, can we still use Mann-Whitney test to compare more than 2 independent groups? Well, Mann-Whitney test is for comparing 2 groups. What we use for more than 2 groups is Kruskal-Wallis test. you can use Kruskal-Wallis test even if the data is not normally distributed, or if the data is not normally distributed. So it is not Mann-Whitney, it is Kruskal-Wallis test. The alternate for ANOVA is Kruskal-Wallis. Those are all the comments that are here. Any more questions? Or yeah, I still have to answer that question on ETA. I will look that up and I'll give a good example in the next one. Any other? Okay, I would like to take a 5 minutes break here because I want a break from talking. So 5 minutes, we will take a break and come back. Yeah, and quickly do a session on sample size. Meanwhile, I'm just putting an online calculator that you can download. The name is, can you see that? Statulator. So you can go online and download. You don't have to download. You just have to keep that active. We can do some examples on Statulator for sample size calculation. Okay, thank you. So after 5 minutes. Okay, so this last session is about sample size calculation. So I've not done much of data science, so I'm not sure how much sample size calculations are actually done in data science per se, because usually in data science you deal with much larger sample size than typical research studies in public health or clinical sciences. So, but this is integral when we are doing, any kind of public health research on, using standard statistical techniques. So, because as I mentioned earlier, it is important to keep a check on the errors, the type 1 and the type 2 error, and which is done through the sample size, through the sample size calculation. So why do we have to do sample size calculation? Now, you doing a large sample costs us time because we have to collect that much more data, and we need more personnel. So it also costs, it is costly in terms of money that you spend for the research. So it is not advisable to do very large sample size studies. And it is also unethical because you should not be putting your study subjects into any kind of unjustifiable trouble for the sake of your research. So it is very important to have an adequate sample size, but not too much also. So what is an appropriate sample size? A sample size that is not very small and not very large. So when we say not very small, the sample size should be adequate to detect clinically important differences. Otherwise, what is the use of doing the study? So that is why sample size calculation is important, to give us that appropriate sample size that is required for your particular studies. For example, today I had a call from one of our clinicians, describing that they are doing a study in clinical oncology, surgical oncology. What is the sample size? So it is very hard for sometimes the practitioners to understand that depending on the context and the type of study that you're doing, actually the sample size could vary. So he has promised to come and see me tomorrow with all the required data to do a sample size calculation. And that is what the approach should be. So, so the question is, if 25% reduction in mortality is clinically relevant, then why sample size calculation? If somebody is actually observing 25% reduction in mortality. But then the doubt is, is 25% mortality reduction in mortality occurring due to chance? And how do we eliminate that chance factor? And for that, sample size calculation is required. And we may calculate that, okay, for observing 25% reduction in mortality to be statistically significant, we need a sample size of 200 in each arm. Then we can say, okay, with confidence that this is clinically relevant as well as statistically significant. So the types of problems that we have in medical health, medical research or public health research can be classified as either estimation problems or testing of hypothesis problems. Now, estimation can be just estimating prevalence or proportion of something, of a disease or so, or it could be estimating the mean and standard deviation of a certain measure in the population. So each of these has a different sample size calculation. Now, if you're testing hypothesis, let us say in a clinical trial, then the sample size calculation is dependent on what is the kind of data that we are measuring. For example, if our outcome is let us say control of BP, so it will be the proportion of people in our sample in intervention group who had BP control versus the proportion of the subjects in the control group who had control in BP. So that's a proportion. Now the comparison of proportion, there is a certain sample size formula as opposed to comparison of means. Suppose you're comparing systolic BP in intervention group versus systolic BP in diastolic group. There we are comparing the mean BP between the two groups, and that sample size calculation is different. So in addition to understanding what is the study design and how how are you actually measuring the outcome, we also have to keep in mind the two errors that I had mentioned earlier, the type 1 error and the type 2 error. So we have to keep the type 1 error minimal at p less than 0.05 and the type 2 error also minimal, because we said that we need sufficient power to detect a difference if the difference is there, and the power of the test is nothing but 1 minus the probability of type 2 error expressed as a percentage. So both of these errors, that is the type 1 and the type 2 error, have to be kept in mind while calculating sample size. So we will look at the simplest of all problems, which is estimating the prevalence of something. So this is the formula. Now here, Z is a standard value that corresponds to a 95% confidence interval. What is really variable here is P, and as P changes, Q will also change. And then what we call as the expected variation, that is the D. Now we'll try to understand all of these a little better in this example. So suppose our study is to estimate the prevalence of vascular headache, and we have some prior data which says that 28% of all headaches are vascular headaches. So that is the data that we have. And based on that, we are trying to calculate a sample size to say that, okay, if 28% is the prevalence of vascular headache, what is the sample size that I need to have for having an estimate with reasonable precision? So my P here is 28%, Q is 100 minus P, so that is the people without vascular headache is 72%. Z alpha corresponding to 95% confidence interval is 1.96. So that is kept standard. And I'm saying I am permitting 10% variability in my estimate. That means my estimate can be lower or higher by 2.8%, 10% of 28. Now, if I use all of this in the formula, I get a sample size of 988, which means that I need to study 188 people with headache to have an estimate of 28% per people having vascular headache with a reasonable precision. Okay, so this is the sample size calculation for single proportion. Now, this is another example of the same problem. So here let's say we are trying to estimate the prevalence of anemia in a group of adolescent girls. In that case, we are looking at prior evidence. What is the prevalence of anemia that has been earlier reported in a similar population? And here we see that the reported anemia prevalence is 29%. Now, based on this, we would like to calculate the sample size. Now, if you could just go to Statulator, if you have already accessed Statulator, so I will just open Statulator here. So that sample size, it's just taking some. So you see 95% confidence interval is fixed. I am going to take my expected prevalence to be 29%, which is what is given in the literature. So this particular paper tells me that the prevalence of anemia is 29%. You can see that here. So I hope you are following this. So since it is proportion here and not percentage, so it is in decimal. So 0.29. And now it is asking, what is the margin of error that I'm permitting? So I earlier said that I will permit a margin of error of 10%. So I will say 0.1, which means that I'm permitting that estimate to be higher or lower by 2.9%. That is 10% of 29%. So calculate, I get a sample size of 941. So I have to study approximately 941 subjects, at least 941 subjects, to estimate the prevalence of anemia to be 29% with 10% relative precision. So that is the calculation. So I hope you did not have any trouble using Statulator. Yeah. So the trick is in identifying which of the different options you should use. Okay, so let's move on. What really happens when we vary, when we have different sample sizes, is that as the sample size increases, you can see that the confidence interval of the estimate tightens. So with sample size of 941, that means you are permitting only 10% error margin. If 10% error margin, then the confidence interval is tight about 29%. So it is 26% to 32%. If it is more error margin, 20% error margin, the confidence interval is wider. If it is even more error margin, 30% error margin, then the confidence interval is even more wider. So that is the disadvantage of having a larger error margin. But sometimes you cannot, if somebody cannot do a big study and really constrained by other factors, then you will go for the higher error margin. But it is not advisable to go beyond 30%, because then you are really permitting too much error in your estimate. Okay. So that's a similar example. Now let's see, what if we are, let me put it in slide. Okay. What if we are interested in seeing the estimating a mean in our study? So for example, instead of asking the question, what is the prevalence of anemia? I am asking the question, what is the average hemoglobin in my population? So let us say the previous studies have reported the average hemoglobin. This is some other example. The average hemoglobin as 10.2 grams per deciliter with an SD of 2.1. Okay. Now, based on this, I want to calculate sample size. Again, the same question. 95% confidence interval. How much is the error margin? The error margin I'm permitting is 0.8 grams per deciliter. So for such an error, what is the sample size that is required? So I go back to my Statulator. I hope all of you can follow me on that. So this option does not hold good now. There are multiple options here. So instead of estimating a single proportion, I'm going to estimate a single mean here. So estimate a single mean expected standard deviation. Expected standard deviation was 2.1. You can see that here, 2.1. So what was that?
Sorry, ma'am.
Yes,
I want to see your screen when you're doing the sample size calculations.
you're not able to see, is it?
No, we can't see it, or I can't.
Oh, I think, oh, yes, I understand. You know why? Because I'm sharing the slide. Okay, I have to shift between that. 1 second. Let me do that. What is this? Can you see this? Can you see
Yes.
this?
Yes.
So let me just show that again. Earlier, I had used this estimate of single proportion, but now since I am trying to estimate the mean hemoglobin, I'm going to use this option, estimate a mean. So the expected standard deviation according to my previous data is 2.1. So enter that there. And I said I am permitting an error margin of 0.8. Okay, which is approximately 10% of the mean. So 0.8, and for that error margin, I need a sample size of 30 subjects. So I need to do the study only in 30 people to have a estimate of the mean hemoglobin. So let me say the person for whom I am calculating the sample size says that actually I can afford to do a few more and have a much more precise estimate. In that case, what I'm going to do is to reduce this margin and error. And let me say, I'm going to say that let my margin of error be only 0.3 instead of 0.8 and calculate. So now I say, okay, if you do the study on 192 people, you will get an estimate for mean hemoglobin with a precision or an error margin of 0.3. That means your actual mean estimate of hemoglobin could be higher or lower by 0.3 grams per deciliter, which is a pretty precise estimate. Okay, so that is how we calculate. Now, these are all estimation problems, as you can see. I will go back to our. Can you see that? Yeah. Okay, so we come back to the presentation. So in this case, yeah, we got using Statulator, we got a sample size of 26. Here we are calculating a sample size of, we got 30 there, I think, but here we are calculating 26. That's fine. That's close. So this is the sample size that is required. So if you reduce your error margin, your sample size will go up. You cannot do much with the SD because your previous literature is telling you that this is the SD. Unless you have another literature which says that this value is different, you have to keep it at it. And typically when you have multiple papers which are reporting different values, then you try to take the paper that is closest to your setting and calculate sample size based on that. And even in your setting, you have, let's say you have 5 papers from your own country and your own region, then you choose the best study that has been done. The most scientifically done study, and that should guide your sample size calculation. And sometimes we choose to keep the higher SD so that we get higher sample sizes. If we have higher sample sizes, we are more likely to have better estimates. So that is the thing. But I don't know about your setting, but in our case here, we have to give a very good justification for sample size when we go to the in institutional ethics committee. The ethics committee has to be, has to be sure that the sample size that we have estimated is appropriate for the study. So they really look at this. So you should have a paper that reports these values, and you should say that with evidence we are doing these calculations. Now that was about estimation. Now let's say we are doing a testing of hypothesis, that is comparing between groups. And the first one that we will see is looking at difference in proportions. Okay, so we are comparing the proportion of percentage between two groups. Let us see an example for that. So we are comparing mortality between high dose and low dose treatment. So we have some pilot data, and the pilot data states that if you give high dose treatment, then the mortality is 16%, 16.7%. And if you give low dose treatment, the mortality is 4.2%. So my question here is, my research question is there a difference in mortality between high dose and low dose treatment? Okay, so for that, you see the sample size formula now has become longer. It is a little more complex. You can also see that in this formula, in addition to type 1 error probability, we are also taking into consideration the type 2 probability. So in testing of hypothesis, the power of the study comes into play. So this is the power part. Okay. Then this is the overall prevalence, and D, the denominator here, is the expected difference between the two groups, or the clinically meaningful difference between the two groups. So with respect to our example, the overall prevalence or the overall mortality between the two groups is an average of 16.7 and 4.2, which is 10.4. Are you able to see my cursor over here on the screen?
Yes.
Yes, it's visible.
So this is 10.4 is the average mortality between the two groups. And this is 100 minus the average mortality, which is Q in our formula. And then we have corresponding to, this is 90% power, because if our type 2 error is 10%, that means power is 90%. So corresponding to 90% value, we have a standard value of 1.282. This is corresponding to our 5% type 1 error. We have a standard value of 1.96. So these are fixed. This is what we have to get from literature or from previous studies. What is the mortality in your setting? The next thing that you need is how much of a difference in mortality can you expect between the two groups? Now you see here, it is 12.5% mortality difference that you are expecting between the two groups. For that difference, what is the sample size that is required? It is 125 in each arm. So you have to examine 125 people who will be given the high dose and 125 people who will be given the low dose to observe a difference of 12.5% difference in mortality and state that to be statistically significant. When you actually examine the data, it is not going to be exactly 12.5. If the difference is greater, let's say it is actually 14 or 15, then this sample size would be very much sufficient for you to state that there is a difference. But suppose the difference when you actually do the study is only 5%, then this sample size may not be sufficient. So you expected in the beginning, before the study, that there will be a big difference. But in fact, when you actually do the study, the difference is much, much smaller. Then your sample size may not be sufficient. So you have to be very clear, careful in choosing these values. So it has to, as I mentioned earlier, it has to be very close to the setting that you are examining. If you are examining high dose versus low dose, you may as well pick the literature from there. Even if it is some pilot data, may as well pick it up from there. Sometimes it is a different treatment. For the same treatment you don't have, but a different treatment. Doesn't matter. Pick it up. You don't have any other evidence for the same drug, let's say you are giving. Then you pick it up from there. So it is very important for you to choose the right kind of literature, to have the correct values here, and therefore have the appropriate sample size. Otherwise, you will do a study and land up saying that I do not have sufficient evidence to state that there is a difference. I'm observing a 5% or 6% difference in mortality, which is clinically important, but unfortunately, my sample size is not sufficient to state that this is statistically significant. Okay, so we will go back to our stat later. Let me just stop sharing and share this once. Yeah, okay. So now we should opt for which one? We should opt for comparing two independent proportions, because we are comparing the proportion or the percentage mortality between two groups, the group that got high dose and the group that got low dose. So it is two groups, and the input that we need to give here is the expected outcome proportion in the reference group. So let us say the reference group is the low dose. It is 4.2. Let me just cross check on the values. So it was 4.2 and 16.7. Okay. So reference group is 4. I hope you are able to follow with me. So 16.7 is 17. So 4% and 17%. And I'm calculating the sample size. It says unmade 99. Now remember, we had specified that the power of the study would be 90%. So by default, in this particular calculator, it takes 80% power, but I can change that. So I'm going to shift it to 90% power. Update. Now you see the sample size required is 127 per arm. So this is the calculation. Now here I have other options of changing this from 0.05. Let's say I want to take it even lower, lesser error, type 1 error. I'm taking it to 0.01. Update. Then I need even more sample size. When my error is reduced, my sample size requirement increases. So now I want 174 per arm. I can even change the sizes. So by default, it is equal allotment. That means the same number in low dose and high dose. I can change this to 2:1 ratio or something like that. That's permitted. And then it does an adjustment and gives the number. So you can try out all of that different options. But so essentially we are comparing the sample size, comparing the proportion between two groups. Let me just share the slide again. Okay. Yeah, so here we are. So 125 per arm to compare to the mortality between two arms. Now let's say we are comparing mean between two arms, not prevalence. In that case, the sample size formula is different. We need the average SD in both the arms and the expected difference in means between the two arms. Again, we will rely on literature. And the literature says that the duration of ICU stay in the study in hours, the number of ICU hours is mean is 61.7 in low dose and 33.2 in high dose. And the SD is almost 90. So based on this information, if I substitute the values for a 28 hours difference in duration of ICU stay, the sample size that I require is about 210 per group for a 90% power. For a 90% power. If I consider 80% power, the sample size reduces to 157 per group. So for comparing two groups for a 29 hours difference in duration of ICU stay, I would need 157 subjects per group. So essentially, the take-home message is that the sample size depends on the question and the type of data, the number of groups that you have, and you need to have content literature before you do the sample size calculation. So if you are doing the calculation for somebody else, please insist on them bringing the right kind of data to form the basis of the sample size calculation. And this is just a table of the different standard values that we use for type 1 and type 2 error. And you can see here that the sample size increases. As the sample size increases, the power increases exponentially. So this is for 0.05 type 1 error, and this is for 0.01 type 1 error. So it is really important to have an adequate sample size for a certain amount of power and type 1 error. Okay, so going back. Okay, now suppose you are doing what is called a cluster study. So what is a cluster study? When you are not, sampling as individuals, but rather sampling as communities. Sometimes you can sample villages into your study and include everybody who is in the village to be a part of a sample. So there is a problem there. Your estimate of variance for the data may be slightly different because you have a group of people who are quite homogeneous with each other because they all form a part of a cluster. And in that case, you have to increase your sample size by using what is called a design effect. So the design effect is calculated as a combination of the size of the cluster, that means the number of eligible people who are residing within that cluster, and what is called the intra-cluster correlation coefficient. So you need to have an idea of all that. And typically in a cluster study, your sample size will increase by either 1.5, which is a design effect, or 2 or so. So you will have to do a rough calculation of what the design effect is and increase your sample size. So be aware, it's just that you need to know about this. So this is of the data. Yeah, so this is to indicate to you as to how, okay, let me not go to that. So I'll show you this. So if suppose we are expecting dropouts from the study, you started off recruiting, say 100 people in each arm, but you're expecting that 5% of the data of the subjects would drop out by the end of the study, then you need to recruit more. So if 125 was your calculated sample size, you should actually be recruiting 132 people per arm, so that at the end of the study for statistical analysis, you would still have 125 subjects per group. So that is adjusting for dropout or any kind of loss to follow, especially in longitudinal studies. This is a note on non-significant studies, a cautionary note on the sample size. So here a study was done to evaluate the scope of community health workers in independently treating major psychiatric illness. So 70 psychiatric patients from 10 villages were identified and diagnosis confirmed by a senior psychiatrist using established criteria. The patients were then assigned randomly to one of the two groups, the first group to be treated by a community health worker and the second by a fully qualified psychiatrist. So they wanted to compare whether a community health worker would give similar diagnosis as a psychiatrist. And the community health workers who had been given 6 weeks training in drug prescribing, etc., were free to manipulate doses and drugs. After 2 months, an independent psychiatrist, unaware of the purpose and details of the study, was asked to evaluate the conditions of all patients, and he concluded that 40% of the patients who were treated by the community health workers had optimal treatment, and 62.8% of those treated by qualified psychiatrists had optimal treatment. And when you do the statistical calculation, you see that there was no statistically significant difference. So what does that mean? Does it mean that the community health workers were as good as the psychiatrists? No, it merely means that there was no sufficient evidence to state that there was a difference between the community health worker and the psychiatrist. So that is why the sample size calculation is critical. Suppose the sample size was a little more higher, then they would have been able to state that this difference of 12.8% is statistically significant. So sample size calculation should be done before embarking on the study, and it determines the number of subjects that should be studied, and the prior literature or research, literature search on the research question being asked is critical in sample size calculation. Sometimes you can even do with the pilot data. So I will stop there, and I can see that there are 2 questions on chat. For now, oh no, sorry. Is the sample size formula dependent on the type of study design? Yes, sometimes yes, because in a cohort study, you would want to do a sample size calculation based on relative risk, and in a case control study, you may want to look at the sample size, calculate the sample size based on odds ratio. Yes, it can be dependent on study design also. And suppose sometimes you have multiple observations, then the sample size calculation should take into consideration. So suppose you are examining somebody's data at 3 time points during the study, then the sample size calculation should take that multiple time points into consideration. So the calculation is different. What determines the precision or the margin of error I choose to use? So it really depends on how much sample you can study. So you can go, so suppose you have the liberty to do a large sample, then you can go for a very small margin of error. But let's say you're doing a small study and you don't have much resources. In that case, you can increase the margin of error and can go up to even 30%. But sometimes this is challenging because when the prevalence of the condition that you're studying is very, very small, then it's really a problem, because for prevalences that are lower than 10% or for prevalences that are more than 90%, the sample size actually increases, because it's just logic. If the prevalence, if there are too few people with the disease in the population, then you have to examine so many people to estimate that few number. So in that case, your sample size will go up. So it is not a blanket rule about the margin of error, but at least between the range of prevalences of 10% to 90%, you can use the rule that you go with the amount of resources that you have. What particular attention is needed when we calculate sample size for randomized controlled trial with multiple specific objectives? Okay, that is a good question. So if there are several questions in a trial and you can pick one particular outcome as the primary outcome for the trial, then the sample size is based on the primary outcome. So the thing is, your sample size should be sufficient to examine at least the primary outcome. And if that number is sufficient for the secondary items, well and good. But at least for the primary outcome, your sample size should be sufficient. So if you can identify a primary outcome, then that is it. But sometimes people can't do that. They will have multiple primary outcomes. For example, if there are biomarkers, they will have, say, 5 biomarkers as primary outcomes, in which case you can do separate sample size calculation for each of the biomarkers and take the larger of the lot as the sample size to go with, so that you are covered for all the outcomes. So that's what it is. But sometimes with many outcomes, you have to be careful that the problem of multiple testing within the same sample, you are testing again and again, which is increasing your type 1 error. So it is always good to really pick 1 or 2 primary outcomes. If you are working with a researcher who is primarily interested, you have to insist on them thinking and carefully identifying 1 or 2 outcomes. And most often on careful thought and examination of literature, they will be able to pick up 1 or 2 and then base the sample size on that. Is it general practice to fix the attrition rate at 5%? No, it really depends on the study. So for example, in pregnancy-related studies, in our setting, we have seen attrition rates as high as 30% because women move during pregnancy. They go to their mother's place and so on. So it really depends on your setting. Suppose you are doing a study which is very short span, let's say for 1 week or so, then maybe you can keep a very small attrition rate. Or sometimes you are doing a study which is very, let's say, an exercise intervention is an exercise. In that case, you can expect a large attrition rate because people might drop out. But if some other interventions, actually there is no much trouble, people are willing to comply, in which case, so it really, the attrition rate would be small. So it really depends on your setting. So I think that's all. Is there any other question? Kelvin, I think there are no more questions. Can we
Yes,
stop?
Doc. I think there is no other question.
Okay. Thank you very much. Thank you everyone for joining in, and hope you have a fruitful course and continue with this, interactive participation. Thank you very much. Thank you, Kelvin, for hosting us.
Thank you, Doc.